People are free to have their cameras on.
Hello, everybody.
Hi.
Hello.
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 Hey, everybody.
Hi, hi.
Hi, everybody.
Hello, everyone.
Hello, everybody.
I feel a little conference homesick this morning, right? Real conference.
Sorry, what did you say, Selma?
That I miss seeing people for real. I see so many faces of people I haven't seen for such a long time. I'm like, oh,
Wow.
I'm remembering moments in nice places around the world.
Hopefully soon.
All right, so I see loads of people have joined now, and it's just past 3, so may as well get going. All right, so hi, everybody. My name is Jonathan Mackey, for those of you who don't know me. See many familiar faces here. And I'd like to welcome you all to the virtual preview meeting, the first part of the IAU Symposium 361, Massive Stars Near and Far. You can see the website link there. Any of you who are not signed up on the mailing list can sign up there. There'll be more information there about the in-person meeting, which we're still hoping to hold next year in May 2022. I just wanted to say a couple of short words about the planning of the meeting. It's been a really long journey, and this meeting has not had an easy path through life, or however you want to say it. Originally, this should have been taking place in Puerto Rico in 2020, but this wasn't possible because of the devastation from the hurricane that happened. So then early January 2018, with Morgan Fraser and John Regan, we put together a proposal to host the meeting in Ireland. And I want to thank the very long-serving LOC and SOC for this meeting, who've been in place for nearly 3 years now. And especially I wanted to thank Anne Grace, who many of you have interacted with last year with paying fees, registering, all of this stuff. She retired recently, and wanted to thank her for all of her work, and also the IT and the finance office staff at the Dublin Institute for Advanced Studies for basically all the extra work that they didn't realize they were going to have from postponing the meeting. And thanks to everybody for being so patient and understanding with when we had to postpone, and organizing the refunds, and everything took a lot longer than we hoped because everyone was working from home and the institute was shut down. But the positive part is that we hope to have part 2 of the symposium around this time next year, 8th to 13th of May, 2022. This is what it looks like all the time in Ireland. So there will be announcements via the mailing list. So most of you, I think, have signed up. We have about 350 people signed up for the mailing list now. Obviously, everything still depends a bit on COVID, but we hope to see everyone next year. And down at the bottom, whichever way you want to see it, hope springs eternal, or die Hoffnung stirbt zuletzt, whichever way you look at it. But we're very hopeful that we can host the meeting next year in person, and everyone can catch up with their old friends and colleagues. And with that, I will hand over to Yorick, who's co-chair of the SOC of the meeting and also president of the Mission G2 for Massive Stars.
Thanks, Jonathan. Yes, welcome to sunny Ireland now. It was raining all morning, but the sun is just coming out. So hopefully we'll have more of that next year, when we will hopefully meet for real. So it's been a very strange year to a lot of us, and ups and downs. And we were we were planning to meet in person, and then also to commemorate, unfortunately, two members of our community, Arik Paudrag and Nolan Walborn, to commemorate their lives and what they've done for science. We'll wait for next year. And then it was the shocking news earlier this year that also Simon Clark passed away way too young, and this has been really devastating news to a lot of us. Then good news as well. Kate McGuire is one of our organizers. She's on maternity leave, so she won't be here today. And our host, Jonathan, maybe he looked a bit tired, but that's not because he's been working so hard, which he's also been doing, but also because he's now a third-time father just recently. So congratulations, Jonathan. So looking a bit wider at our commission, I think it's been actually quite a good year, thanks to Ulysses. There's this big project on the Hubble Space Telescope, 1,000 orbits on young stars, and 500 of those for massive stars in low mass galaxies. So that will be an asset for our community for a long time to come. And we have also obtained complementary optical and infrared data with X-Shooter on the VLT. And we have had some meetings, and already 100 people have signed up via the KU Leuven website. So that's another big thing this year, that we have hosted a new website. So thanks to the people at KU Leuven for being able to host the Massive Star newsletter there. And I would also like to thank UNAM, and in particular Philip Einens, for hosting the previous Massive Star newsletter for the last 25 years. It was a very good idea, and it's been very successful, and it has brought us together in many ways. Hopefully the new website and the new new Massive Star newsletter will do the same, and it will help us communicate our results more quickly to each other, and hopefully to have real meetings. So with that, I think I'm going to hand over to our Zoom master this week, Morgan Fraser.
Thanks, Jörg. So yeah, I just want to outline some of the practical aspects of this meeting. So first of all, as Jörg and Jonathan said, it's great to see so many people, and you're all very welcome. So first up, to let you know, we're recording the talks. So we hope to make them available online maybe next week sometime. If you're a speaker and you don't want to be recorded, or you have something that's under embargo, you don't want made public yet, please send us an email and we can edit out your talk from the videos. If you're a participant, I would suggest to keep your camera off, and if you want to ask any questions, just put them in the text chat. So all of the talks are 12 minutes long, and then they'll be followed by 3 minutes of questions. So our schedule is quite tight, so please don't be offended if our chairs are cut you off quite brutally. If you want to ask a question, you can click on the raise hand icon. So this is just at the bottom of Zoom. If you click on reactions, you can see a little button to raise hand, and then the chair may call on you. Alternatively, you can type out any questions in the chat box. And we might also take some questions from the Slack channel if there's some interesting discussion happening there. If you're not asking a question, we'd ask if you can keep your mic muted, because there's a lot of people on the call. I see a lot of people have signed up for the Slack, so I think there's well over 100 people in it now. So we'd encourage you to join, and hopefully we can have some more lengthy discussion there, along with that after each talk. If you haven't joined the Slack, details are in the email you received a few days ago. And then finally, at the end of the meeting, so after the discussion, we're hoping to have some sort of a social event. So how this is going to work is we are going to all stay, if you want to, you can stay on the same Zoom channel, and we're going to open a number of breakout rooms that are organized by theme. So there's one on supernovae, there's one for PhD students, there's one on mass loss rates, And you can pick and choose which one you want to go into and talk to people in smaller groups. So that's everything. Finally, if you have any technical problems with Zoom or Slack, or any issues connecting, or indeed any other problems or anything you want to raise, please don't hesitate to contact myself or any other member of the LOC. Otherwise, I look forward to an enjoyable week of meetings. So I'll hand over now to the first chair of our first session, who is Fabrice.
Yes, thank you, Morgan, Jonathan, and Yorick. So I'm Fabrice Martins, for those of you who don't know me, and I will be sharing the first session today. So we have 4 talks. As Morgan just reminded us, it's 15 minutes divided in 12 plus 3. So I will let each speaker know that after 10 minutes that they have 2 minutes left. So the first speaker is Mikhail Abdulmasi. If you could share your presentation.
Sure. Can you hear me?
Yeah, perfectly.
Okay. And do you now see my slides full screen?
Yeah, I do.
Perfect.
So please go ahead.
All right. First, I'd like to thank the organizers for giving me the opportunity to speak with you all today and trusting me with the first presentation of the conference, even if it might have something to do with my last name. My name is Michael Abdulmasi. I am a postdoctoral fellow at ISO in Chile. And today I'd like to talk to you about a new 3D spectroscopic analysis technique that we have developed to study non-spherically symmetric massive stars. So deviations from spherical symmetry are common in the lives of massive stars. We know that a majority of massive stars are found in binary systems, and that binarity can be characterized by interactions, and these interactions often lead to deviations from spherical symmetry. As the stars begin to fill their Roche lobes, they'll begin to get more and more deformed until eventually they begin to overflow or come into contact, etc. Even in stars that are more distant, or even single stars, rotation is also a very important aspect of massive star evolution. And rotation is also characterized by deviations from spherical symmetry, and these become very important when we consider how these deviations from spherical symmetry affect the observations or the parameters that we derive from these stars. So consider a rapidly rotating massive star. As it begins to rotate more rapidly, the centrifugal forces will cause the equator to bulge out a little bit while the poles will stay where they are. And this change in radius across the surface leads to a change in surface gravity, since the mass of the star isn't changing. And this change in surface gravity across the surface leads to a change in temperature. So here I have plotted a rapidly rotating system and an over-contact system, and here just kind of how the temperature changes across the surface of the star. So you have very warm poles and very cold equators. You can also see this in the contact system, maybe not quite as obvious, but you can see this is an inclined system, so you can see the pole here and the cooler equator here. So these surface variations lead to very interesting observational effects that we often neglect. So let's take a look at this in a little bit more detail. So if we consider the same rapidly rotating system, and we look at it at different angles, if we look at it at 90 degrees or edge on, we're seeing a very large portion of the equatorial region. Whereas if we're looking at it pole on at an inclination of 0, we're seeing the much hotter polar region more predominantly. So if you were to look at this same system and measure its temperature from spectroscopy from this angle and measure its temperature from this angle, you might measure 2 different temperatures, while intrinsically the star is not changing. The only thing that's changing is the angle at which we are viewing this star. So this effect often isn't accounted for in our spectral fitting techniques. To fit massive stars, we need an NLTE radiative transfer code, and the ones available at the moment are mostly in 1D. So we have FastBin, CMFGen, Power, TMAP, etc. All of these are 1D NLTE radiative transfer codes. So they have to assume that your star is a sphere. So to approximate this non-spherical object as a sphere, you need to take some characteristic radius, some characteristic temperature, some characteristic surface gravity, and then you get the parameters for that system. Now this becomes even more I guess, emphasize when you're looking at a contact system, for example. So before we can actually do the analysis, we first need to disentangle and separate the spectral contributions from the primary and from the secondary. And then we fit each individual one with the atmosphere models. And this disentangling assumes that we have two spherical stars in a binary system. And then the atmosphere fitting, we are looking at each star individually. So now we have two separate single star systems instead of one contact binary system. So all of this temperature distribution across the surface and the geometry of the system is completely neglected when we observe a system or when we analyze a system in this way. So how can we actually improve our analysis? So really what we need is we need to accurately model the geometry of the system. We need to accurately model the surface variations of the various parameters, and we also need an appropriate radiative transfer code. And to do this, I'm using Phoebe, which is a Wilson-Divini-like eclipsing binary light curve modeling tool, and the 1D NLT radiative transfer code FastWind. So we combine these two to form the spectroscopic patch model for massive stars, or SPAMs. And this is really a four-step process. First, based on the binary and stellar parameters, we generate a mesh. So based on the mass, the radius, the separation, etc., and using Roche formalism, we create a three-dimensional mesh of the system. Then we populate the mesh with local conditions. So here I have plotted temperature, but for example, we also have the surface gravity, the local radius, the radial velocity of each individual point across the surface. And then we assign FastWind models to each individual patch across the surface, corresponding to the local parameters at that patch. And then we integrate over the visible surface at this given phase or orientation. So now, instead of approximating our overcontact system with two spherical models, two spherical FastWind models, we are using hundreds or even thousands of FastWind models across the surface to represent this object. And this really allows us to both account for the geometry as well as the differences in temperature and other parameters across the surface. So now that we have a way to actually model systems in more or less 3D, let's look at how accounting for these 3D processes affects the observed spectrum. So here I have in black a FastWind model plotted, and in red a SPAMS model plotted for a system with the exact same parameters. So I have the same abundances, the same temperature, and everything. The only difference is the geometry. FastWind is assuming spherical, while SPAMS is allowing for distortion due to rotation. And here I've plotted two helium lines, a helium-1 and a helium-2 line, and the ratio of these is often used as a temperature diagnostic for massive stars. So as we can see, as the inclination changes, while the ratio is not changing for the spherical case, it is changing quite a bit for the rotationally distorted case. And this is telling us that if we don't account for these 3D processes, these 3D geometries of these systems, then the temperature that we might measure could be wrong. So can we actually observe this affected real stars? So here I have three overcontact systems, and the reason I'm choosing to look at this in overcontact systems is that we need to really observe this, we need to know what the inclination of our star is. And contact systems are nice because their light curve allows us to nicely get the masses of the two components, the inclination, the radii, etc. So, and we know that from these systems that they should be tidally locked because of how close they are. So we have an idea of what the rotation rates for each of these systems are. So here, V382 Cygni and SMC 108086 both have inclinations of above 80 degrees, whereas VFTS352 has an inclination of 55.6. So from this, we would expect that because these two have high inclinations, that we're seeing more of the equatorial region, and that if we were to measure the temperatures of both components with 1D models, we would expect to find a lower temperature than if we were to measure it with 3D models for V382 Cygni SMC 108086. For VFTS352, it's inclined a little bit more, and we're seeing more of the hot pole, so we might expect that the temperatures are closer to one another with the two techniques. So if we do actually do this exercise and we fit them with 1D techniques in blue and then SPAMS in red, what we find is that for V382 Cygni and SMC 108086, we do see a definite change in the temperature and luminosity between the two techniques, whereas for VFTS352, SPAMS and the 1D both give you relatively the same temperature. So these sources are rotating at about 300 kilometers per second, and we can already see this, which in these cases is about 50% critical. So this is showing us that if we are not taking into account this geometry, then the evolutionary interpretation that we might get from the temperatures that we derive could be wrong. So let's see if we can actually quantify this. So I'm going to take you back to our rapidly rotating system, and now I'm going to actually tell you what the temperature is across the surface. This is that 40 kilokelvin star that's rotating at 90% critical that I showed you in the previous slide. And here you can see how the temperature changes across the surface. And we have almost a 20,000 Kelvin difference in temperature between the pole and the equator. So if we were to calculate a SPAMS model for this source at various inclinations, and we were to simulate a signal to noise of 300, and then we were to fit them with 1D models, or with 1D techniques, this is the temperature that we would derive. And as you can see, the temperature changes quite a bit as you change the inclination. Now, the star itself is not changing. It still has a temperature of 40,000 Kelvin. However, the temperature you measure from the 1D techniques can be almost 3,000 Kelvin off at an inclination of 0, and almost 2,000 Kelvin off at inclinations of 90. Really, the only place where you get similar temperatures is at an inclination of just about 60, that magical 60 degrees in astronomy that seems to pop up everywhere. However, if you're outside of a very small range around there, then you are more than 3 sigma away from your real temperature of the system. This goes to show that if we don't account for this, then again, the evolutionary interpretations that we get from these systems can be completely off.
2 minutes.
Thanks. I've been focusing mainly on over-contact binaries and rapidly rotating systems, but there are many other applications of SPAMS that I haven't mentioned that this can be applied to. For example, heartbeat stars, semi-detached binaries, even just your regular run-of-the-mill binaries, some effects in there, such as the Struve-Sahara effect and the Rossiter-McLaughlin effect, which is shown here. So you have a rapidly rotating system and something eclipsing it, and you can see how when it's covering the blue parts of the star, you're seeing part of the blue part of the line being blocked out. And then as well as pretty much anything that Phoebe can model, we can model with SPAM. So fairly soon triples and multiples will be supported by Phoebe, as well as pulsations. So we'll be actually able to model the line profiles of pulsating stars. So I'm going to stop here, and I'm going to thank you very much for your attention.
Thank you, Michael, for a nice presentation and keeping on time. So we have time for questions. If you have a question, please raise your hand. In the meantime, I may ask myself one question. So you showed that for rapidly rotating star, the effects are important. I was wondering for binary system, do you know how close the systems have to be so that this effect, the deformation, is important?
For Roche distortion, I'm not exactly sure how close they need to be before this becomes important, but that's something that that I'm working on. So that'll be something that I'll see in the future. Really, I mean, it really comes down to how big of a temperature distribution you have across the surface. So I mean, if the temperature distribution is fairly small, then obviously the difference in the 1D to the 3D temperatures is going to be small. So it really comes down to how distorted the star is. So yeah, that's what I would say.
Okay, thank you. So we have a first question by Artemio Herrero. Artemio, please. Can you unmute?
Yeah. Thanks, Michael. Very nice talk, by the way. I have 2 short questions. The first one is concerning the same effects over on the gravity, whether you find the same effects on the gravity, and the second one is whether you have determined more or less what is the effect when you change the spectral, so the temperature, basically, if you get the same effect at lower and higher temperatures.
Sure. Yes, we do see the same thing for the surface gravity. I didn't show that here, but yes, we do see the same effect. You'd see lower surface gravities when looking at an inclination of 90.
But the more or less the effect, the range of the effect, 0.1, 0.2.
It depends on how rapidly rotating your system is and at what inclination. It can be fairly large. It can be 0.5, 0.6 at some of the most rapidly rotating systems. So it can be quite a large effect. What was your second question again? Sorry.
The variation with the temperature, whether you get the same.
Yes, yeah. So what I've showed here is based on the ratio of the helium-1 to helium-2 lines. So obviously, as you get to higher temperatures, you're going to be dominated by the helium-2, and this error bars are going to be larger. However, if you use other temperature diagnostics, such as the ionization balance of other ions, then you can do the same thing. So at lower temperatures, when you stop seeing helium-2, then you can start using the ratios of nitrogen abundances, etc. So as of right now, I've only looked at the helium-1 to helium-2, but you can do this for any set of ions that's characteristic for the given temperature range.
Okay, thank you. So I'm afraid we are running out of time. So there are 3 more questions. Please, can you ask them either on the Slack or on the chat channel? And Michael, can you please answer these questions? Sure. So thank you, Michael, again. And can you unshare the screen?
Yep.
Okay.
Thank you very much.
Thank you. So we are moving to the second presentation by Claudia Agliozio.
Okay. Hello. Can you see my screen?
Yes. So Claudia.
Okay, perfect. Okay, so I'm Claudia Agliozio. I'm a postdoc at ISO. In this talk, I'm going to discuss the case of dust in nebula around the luminous blue variable stars and their potential role as dust producers in galaxies. But first of all, what are luminous blue variable stars? This is a difficult task to summarize what are these stars in one slide, because the topic is quite controversial, as you may know. However, in the classical scenario, luminous blue variable stars are unstable blue supergiants. So we are talking about stars that occupy the upper part of the HR diagram. Now, because of different types of instabilities, LBVs show different types of spectroscopic and photometric variabilities. And usually these are associated also with variable mass loss rates. The main variabilities are the giant eruptions and the Storado-style variabilities. In the literature, you can find several models that were formulated to explain the physical mechanism behind these instabilities, but they are mostly under debate. However, we want to focus for this analysis on the mass loss rates. So when the stars are quiescent, so basically they are blue supergiants, the mass loss rate is driven by radiation pressure on the metallic lines. And the theory of stellar winds predicts that the mass loss rates scale with the luminosities, among other parameters. So for the range of luminosities we are interested in, basically the expected mass loss rates vary between 10 to the minus 7 to 10 to the minus 5 solar masses per year. When the star manifests the LBV phenomenon, we observe mass loss rates increased by at least a factor of 3. This is the case of the Storado variables, while instead, in the case of giant eruptions, the mass loss rates are increased by several orders of magnitudes. Now, as you may know, giant eruptions are very rare in our galaxy. In the 19th centuries, there have been observed 2 giant eruptions. The most famous was Eta Carinae, which basically in very few tens of years, this star released a large amount of material, forming the so-called Homunculus nebula. And a large fraction of this mass is in the form of dust. Now, the question is how such hot stars with such a hostile environment can form dust. This was explained 10 years ago by Gojanek, who found analytically that the required temperature and particle density to form dust are met for mass loss rates above 10 to the minus 2.5 solar mass per year, which are the mass loss rates expected in giant eruptions. Now, several galactic but also Magellanic Estorador variables and other candidate LBVs show massive and dusty circumstellar nebula, suggesting that they may have experienced a giant eruption in the past. And so suggesting that this phenomenon may be more common than what previously thought. There are other mechanisms for dust formation to consider, and one is in colliding winds or close binaries, like the case of some warfare stars. And this could be also, as an example, the case of the LBV binary HR Carinae, which has an inner nebula that resembles a pinwheel-like nebula. Now, because of the nature of these eruptions, a long time ago it was proposed that the LBV mass loss can be independent of metallicity. And so LBVs were also suggested as potential dust factories at a high redshift, so at subsolar metallicities. This scenario was never tested. However, the Magellanic clouds are an ideal laboratory to test these scenarios. Why? Because they are relatively close, the uncertainties on the distances are more accurate than many galactic objects, and because of the solar metallicities. So for the rest of the talk, I'm going to focus on the Large Magellanic Cloud only. Here we have the so-called dust budget problem. So basically, far-infrared Herschel observations revealed a large amount of dust in the galaxy. This dust mass cannot be produced by AGBs because these, despite they are possibly more numerous, they have a dust injection timescales which are comparable to the age of the LMC, so they cannot have produced so much dust. So it was suggested that dust forms mainly in the ejector core collapse supernova, like the case of supernova 9087A. But we expect also a fraction of the newly formed dust to be destroyed by the reverse shock. And this talk I'm going to show you that LBVs are also important. So the Large Magellanic Cloud counts 27 confirmed candidate LBVs. This is according to the most recent census compiled in 2018. So we collected all the infrared images and the photometry from the catalogs in the infrared domain. And the first thing we did was to revise the LBV status on the basis of the infrared ACDs. We found that our objects can be divided in 4 classes. Class 1, which is the class with the class more numerous, represents confirmed candidate LBVs that show not only a strong ionized stellar wind in the near infrared, but also an excess of infrared emission due to a thermal dust component, usually peaking between 24 and 70 microns, so suggesting an extended warm dusty nebula. Then we have class 2 objects. These are confirmed candidate LBVs, presenting in the ACDs only a strong emission due to free in the ionized stellar winds, and the 24 micron point usually agrees with the power law of the stellar wind. So we don't see in these objects an excess due to dust. Then we have class 3 objects. These are all stars that in the literature were classified as supergiant B bracket B stars, which are in the LBV sample because they present some other commonalities with LBVs. So these stars are known to have a hot, dusty, long-lived disk And they have a very distinctive ACD shape compared to the other LBVs and candidate LBVs. Suggesting the formation of dust, a mechanism of formation of dust different from the phenomenon we analyzing here. So for the following analysis, basically we exclude these objects. Also, we exclude the class 4 objects because these are stars that present in the ACD, the only stellar photosphere. They don't show any ejecta, and we find also that in the literature they were flagged as non-candidate LBVs. So to determine the dust mass, we need the long wavelength photometry. To increase the sensitivity at long wavelengths, we performed the stacking analysis. So then we fitted the resulting photometry with a gray body for the dust and a power law for the wind. We can see that the integrated ACD shows the typical ACD of an LBV with a strong ionizing wind and a warm dust component in an extended nebula. The integrated dust mass that we find is on the order of 0.1 solar mass. However, in the future, this total dust mass may be even larger if we assume that class 2 objects are stars that didn't experience the giant eruption yet. So now the most challenging part of this analysis is comparing the LBV dust mass with the ISM dust mass. This is due to the fact that our sample doesn't represent the entire population of LBV stars. And because, okay, the LBV phase is very short, but in general, massive stars' lifetime are very short. And we don't know how many of these stars become LBV or they manifest the LBV phenomenon. Anyway, we consider the star formation history in the LMC by Harris and Zariski. You can see that the star formation rate weren't constant throughout the lifetime of the LMC. We assume for the initial mass function 2 slopes, the salpeter one, which is more ideal, however, for the solar environment, and the slope by Schneider et al., who found in the 30 Doradus star forming region an excess of massive stars. So in the assumption that all OB stars become LBVs, over the LMC lifetime, we find in the two cases this range of masses, which, if you see, it's a significant fraction of the dust mass inferred from the global entire galaxy.
2 minutes.
Thank you. So in these calculations, we are not taking into account the dust destruction by the subsequent supernova. However, there are several arguments that we make in favor of dust survival. One is that this nebula are massive, so the nebula may slow down or even stop the blast wave early enough. Then the observation suggests that these nebulae contain large dust grains. So these large dust grains can survive the sputtering. The grains are often spread at large distances from the star. The nebula are often clumpy and asymmetric, and all these arguments in favor to the survival of dust. And then finally, we have also the case of supernova 1987A. 30 years after the explosion, Mikako Matsura et al. Found hints of dust reformation or grain growth in the progenitor circumstellar nebula. In the literature, there have been several efforts to try to estimate the dust survival in the reverse shock, so the survival of dust formed in the supernova ejecta. And these studies usually show the survival rates vary between 40 and 80%. A recent work showed that wind-driven bubbles created by the progenitor can create also the conditions for dust survival. And finally, another recent work that showed that under certain conditions, the implantation and trapping of ions can counteract grain destruction by sputtering. So summarizing, we refined the sample of luminous blue variable stars in the Large Magellanic Cloud based on the infrared CDs. We measured the dust mass of present LBV nebula, and we estimated the potential dust yield of the LBVs in the Large Magellanic Cloud. There are, however, two important uncertainties that in the future we have to be addressed. One is the fraction of OB stars that manifest the LBV phenomenon, and the other one is the dust destruction by supernova. And with this, I conclude and I take any question.
Thank you, Claudia. So we have time for a couple of questions. Are there any, either in the chat or Slack? No questions? Yes, there is one by Lieke Vanson, please.
Hi, yeah, thank you. Very nice talk. I was wondering, I think you assumed that the fraction of OB stars becoming LBVs was 100%.
Yes.
So you say this is an uncertainty. How high do you expect the fraction of OB stars to become LBVs actually?
I can only guess because I think so. One way would be to compare the number of LBVs with the the present LBVs with the present OB stars. But I think there aren't works that obtained completeness of OB stars in the Large Magellanic Cloud, right? I think some recent work, I apologize, I'm not remembering the first author, and considered around 90 OB stars, but they didn't claim a completeness. In that case, it would be around 20%. But unfortunately, I really don't have this number, and somebody here can give me some useful number. I would be happy to include in this analysis.
Thank you.
There's another one by Paul Crowder. Paul, please.
Yeah, just to follow on from the last question. So, well, I guess we have to be careful about talking about all OB stars, because of course B stars all the way down to a few solar masses. But if you had a threshold of, let's say, around 15 solar masses, there are, I would say, at least 5,000 O stars and early B stars in the LMC. So a very large number of OB stars, and so therefore, if they all pass through an LBV phase, the LBV phase would be, of course, extremely short, given that there are of order, a dozen or so confirmed LBVs, or rather the phase in which they are variable is very short.
From the IMFM, I considered lower limit for the mass of 25 solar masses. So can you give a number for more massive stars?
So I guess you would be looking more than of order of 1,000.
Mm-hmm. Okay.
Something in that ballpark. I guess my question actually was more about the fact that you have clearly LBVs, some LBVs, let's say, within star forming regions. Now, not all of them, of course, but some are. And so you have some confusion often between the dust from the LBV nebula as opposed to dust which is associated with the general star forming region. I'm thinking about R143 in particular.
Yes.
So that must be a bit of an additional uncertainty in terms of association of the dust from the LBV as opposed to just co-located.
Yes, so actually the stars that suffer more confusion are in fact R143 and R85, sorry. In this case, we notice that we don't get a good photometry from the stacked image, and we derive at the lower limits by excluding them from the stacking. So, however, in general, as you said, there could be contribution from ISM, but we find warmer temperatures than the ISM.
Okay.
But of course, in the future, high resolution images in the infrared will be useful, because with the space telescopes, we can get in the infrared the best 5 arc-second, which is comparable to the size of the most extended nebula in the Large Magellanic Cloud.
Thank you. I'm sorry, we have to stop here. We can
Okay.
continue the discussion on the chat or on the chat or Slack. But thank you again, Claudia. So now we're moving to Maslow's predictions with two talks. The first one will be by Joachim Bechtel-Lehner on Maslow's near the Eddington parameter. So Joachim, please.
Okay, good afternoon. Thanks to the organizer to give me the opportunity to talk here at the preview IAU symposium. Currently, I'm a postdoc at the University of Sheffield in the group of Paul Crowder, and I will talk about Maslow's prediction as a function of the Eddington parameter. So the general motivation is to understand massive stars and the stellar evolution. So there's a lot of things going into the stellar structure calculation as well as population synthesis model. Just from basic physics to mixing process, reaction rate, chemical composition, masses rate, and also reactive mass ejection, what we heard at the moment. Also the binary evolution, which intensifies the complexity as well as magnetic field. And then also basic measurable, observable parameters like mass ratio period, eccentricity, rotation, play also an important role. So and this flows all into stellar structure and evolution models, which then be combined, also feeds in the further step in the population synthesis models, which are then used to actually interpret star-forming galaxies and high redshift galaxies. And the most massive stars basically dominate the ionization as well as mechanical feedback. So if you now look on the Maslow's, dominates actually the evolution of the most massive stars for stars around 60 solar masses and higher. And those masses rates are usually under-predicted in stellar evolution model as well as population synthesis model. And then if you look on the recent publication only for 2021, you can see this is a really huge hot topic still in massive star research, not only on main sequence, but in particular also in the post-main sequence. So as you know, the mass loss depends on the Eddington parameter, and the Eddington parameter is basically defined as the gravitational force, a radiation force over the gravitational force. And if you only consider the electron opacity, then you have this Eddington factor as a function of gamma E. And the nice thing about the Eddington parameter is for gamma E, if the atmosphere is fully ionized, then it's basically independent of the stellar radii, and as well as an L over M, which is an important quantity in stellar structure evolution codes, as well as observational. You can also parameterize it as a function of effect temperature and surface gravity, which makes it a very neat Maslow's description if it only depends on the Eddington parameter. And what you can see, so the masses rate for optical thin wind, so basically all stars follow to 2.7, and then at some point the mass loss dependence increased to an exponent of 5.2, which was observational found already a couple of years ago. Now, if you look in the mostly wide used mass description by Wink et al., we can see there's actually no gamma dependence in the mass loss description. Yes, in mass term, but also an L term, but not a direct dependence on the Eddington factor. And the masses rates are then over-predicted for the most massive stars, while over-predicted for the less massive stars and over-predicted for the most massive stars. So if you go really wide back to the mass loss formula from the CAK wind theory, they have a mass loss Eddington parameter function, but also has still a mass loss term in it. And if you try to fit this as a m dot over m, then you can see that actually the 1 minus gamma, which actually the sudden increase in the masses rate only occurs at very high Eddington factor. Also, the mass is in this term is just a term, but it doesn't actually represent how the mass luminosity relation changes for the most massive stars. So for the less massive stars, L is proportional to m to the power of 3. And if you go increase the stellar mass, also the stars getting closer to the Eddington parameter. So the mass loss, mass luminosity relation has to become linear, otherwise it will cross the Eddington limit. And this is not represented in it. And if you just flip this plot around, then you can see here you have L to the power m3, which changes in the L proportion to m, which is very similar to the mass loss rate Eddington factor relation, what we found in the previous plot. So in the new mass loss description actually takes this idea and modifies the original CK master's description. So if you take the Eddington stellar model, which is basically a fully radiated star, and if you for small Eddington parameters, L is proportional to M3, and if you approach the Eddington limit, L becomes M. And if you derive it, then you can derive M as a function of the Eddington parameters. And you can nicely see if you combine the CK with the Eddington stellar matter that you have an additional square term in 1 minus gamma relation plus a 1/2 term in the linear relation and equation. So if you now write it in the log scale, you have here an M0, which merge all the constant in it. Alpha is the CK alpha frost parameter. And then you have here this relation for the optical Singh machine. And this is probably when you go close to the gamma, when both terms, also this upper term and lower terms, equate. This I define as a gamma transition mass, transition Eddington parameter. So if you use now the same data, which I showed in the previous plot, and then you can see here the regime for the optical Singh regime, and you have here for the most massive stars, which has the gamma to the 5.22 dependency. And you can see that this mass description actually can fit not only the optical Singh regime, but also the optical Singh regime in one single relation. And then also, if you define the gamma E trans, which is defined previously, you can see that it actually occurs in the transition from optical thin to optical thick winds. And this is actually really great because then you can able to calibrate your master state. So to brief summary, so the gamma transition Eddington parameter occurs at the optical thin to optical thick, and then you can actually calibrate it with the massless transition master state defined in Wing and Krasner et al. 2020. So the only thing what you have to know is alpha, and if you know alpha, you know the transition master rate using the description by Wing and Krasner, and then you can also derive an active clumping factor by just moving up and down this relation, also basically M0. And this I have done for a sample of massive stars in the cluster R136. Now for this regime, I derive an alpha of 9.4. And then transition Eddington parameter of 0.47. And this provides the following relation. As in the optical Singh regime, you have gamma of Orion to the power of 3 and 1 minus gamma to the power of 3/2. And then if I use the transition master rate, I derive a clumping factor of 0.25 plus minus 4 minus 0.15. This is from clumping factor between 2 and 12, which is basically consistency. And then also again, the transition from optical thin to optical thick for gamma E trans, of course, again, from optical thin to optical thick masses rates. So now, if you look on the materially dependent of this mass Eddington relation, you can see, also Joe Puls 2000 in his review paper actually showed that alpha is metallicity dependent, so it's decreasing with decreasing metallicity, which also means that the transition from Eddington factor goes to higher Eddington parameters, which means the L over M ratio has to be larger, which is consistent with the idea that, in metal poor, you have less wind driving, so require a higher L over M ratio to become optical thick wind. And you can also see that in general, for the optical Singh wind stream, the slope is much steeper, as well as the 1 minus gamma dependence as well. So for different metallicity, you should expect different slopes on the gamma E dependence. Also, when you look at the wind momentum luminosity relation, you can see that as a reference, I showed the Wing master description. You can see that they are under-predicted for the high master states and over-predicted for the less luminous stars. And also the slope of the VLR is proportional, it is equal to 1 over alpha, which is the alpha force parameter, which is already from Kudryavtsky et al. In 1999. And if you just take this, the slope is 2.4, and then your alpha is 0.41. So even though you only may have an sample of only an O-star winds in maybe in really metal poor galaxies like Sexton A, you only need to determine alpha either through the M dot gamma fit or just through the wind luminosity relation. And you can derive an alpha, and then you also have basically on this, you also have to can calibrate then your absolute wind moment, also a master rate scale for your master's description. Now to summarize, also the new CAK type master frequency can explain m dot and the gammas and gamma e and keeps the simplicity of the CAK. So it's nothing really special on it. It's just simple fitting. And it's not only, it can able to predict O as well as the enhanced master state of the most massive stars, the main sequence for Fourier stars. And once you have derived alpha, then you can actually derive all the other parameters as well and just calibrate the absolute master scale using the transition master rate. And this, which sets the master rate overall times scale where master should be depending on metallicity as well. So thank you very much.
Thank you, Joachim, for a nice talk and also for being ahead of time. So we have time for a few questions. So yes, Joachim Bulls, Joe, please. You need to unmute yourself. Yeah.
Yeah, I have just seen it. So Joachim, thanks a lot for this very nice talk. I think the results from this talk have one big advantage, namely that they do no longer make the difference of the wind features as a function of the optical depth, which more or less always refers to the continuum and not to the lines. And it was always not so much clear in the original version, so to say, of optically thick and thin winds, what the continuum has to do with a different kind of line driving. As far as I have seen it here now, it's more the question that at first we have the gamma E, of course. This is clear, that's the old idea, as well as a different relation between luminosity and mass. So that's a big advantage. Just one warning. I mean, all this, of course, assumes that in these massive O stars and main sequence Wolf-Rayet stars, we still have the same mass driving as in the normal O stars. That's the major point, so that the mass loss is not related to some sort of iron opacity bump or something like this. So this is the major question. One could also say it the other way around. If all this would be true and so on, then all these stars are just normal, so to say, O star winds. Do you agree?
Also basically, I think I would say agree, but if you look already on this plot, yeah. Depending on, you would also assume that maybe here this alpha might be a bit different to the alpha over here. So what I really do is an effective alpha. And if the opacity, the item peak opacity really contributes to it as well, then you would assume, yeah, basically overall change over it. But if you look at source plot, the fits are surprisingly good. So at the moment, but just looking on the source fit, I wouldn't see a problem yet, but it might be depending also on if it's an O supergiant or an O dwarf. If you also go down to the less luminous stars, maybe alpha is changing.
Yeah, what I meant is here, I mean, all this still refers to the old CAK theory, and this means that the mass loss is more or less purely initiated by the radiative line driving. So, of course, with respect to gamma E. Whereas when you have a Wolf-Rayet star or so on, a classical Wolf-Rayet star, then you might think that the line driving for the mass loss itself is almost irrelevant. So this is a different mechanism.
Yeah, I think Andreas Sander in his 2020 paper actually compared this one. Actually, it works for some type of classical Wolf-Rayet stars, but not for the less luminous ones. Yeah. But this is just because of the very simplistic parameterization, I would say.
Thank you.
Okay, so we have another question by Laura Murphy.
Hi, thanks for the lovely talk. I just wanted to ask about if you have a relation for how alpha changes with metallicity. You say you can get it from the observations, but say for very low metallicities where you don't have those observations or even zero metallicity, is there a relation that you can use there?
So if you want to calibrate it of different metallicity, which will be done with Ulysses, or I will do it with Ulysses, then you should see alpha changing from the LMC to the SMCs also for the archival Milky Way data. But you don't need a large sample of stars which also cover the optical thick-wind regime. The advantage is you can rely on the O stars and B stars, because once you know alpha, you can actually know the transition massless rate over here. So you can calculate based on this without knowing this over here. And I think that's the beauty of this massless description, I would say.
Okay, thank you.
Okay, we can take one last question by Luka Poniatowski.
Yes, hello. Thank you for nice talk. I had question regarding alphas. Yes, here you mentioned that alpha depends on metallicity, but alpha is also something that depends on general distribution of lines, what species you have, how they are excited, and so on, which can be computed. But now you can also fit that. How does that compare to general values of alpha that are normally used in literature? For instance, one of the famous numbers is 2/3. How does it compare to alpha derived from the different ways?
So one is 0.6, but it's also depending if you have this delta parameter in as well. But this one is alpha, just alpha effective, and this alpha count basically for all type of stars. It's an average value. It should be supposed to be a bit lower than your alpha, 0.6 or 2/3, which also has this concorrection of minus delta included. So if you include the delta parameterization as well, then alpha would also go a bit up. But I want to keep it as simple as possible. But if you look in the Paul draft papers, which introduces this parameterization, this EIK formula is not simple anymore. It's highly complex, and you can't parameter it in that way anymore. But for this massless description, I would say it's sufficient, and it's at the moment I think one of the best which can actually connect wind, optical thick wind as optical thin wind in one nice formula. And this is, I think, we have to focus on this one. And for stellar evolution models, if you want to implement it, I think this would be the straightforward way, because otherwise it would be too complex to execute, or not impossible to use it and calibrate it.
Okay, thank you, Joachim, again. So we have to move on. And to the last talk of this first session, and that would be by Robin Björklund, again about new prescriptions of massless rates for O stars. Please go ahead.
Yes, thank you. So my name is Robin. I'm a PhD student at K11. And I mainly now want to talk about how we are using detailed atmosphere and wind models to derive massless rates for more than just O stars, which is still on the schedule, but also for B-type stars and for other massive stars, and see how it influences their evolution. So I want to iterate again on how mass loss can be important for massive stars. It's a key uncertainty in many evolutionary stages. And it's important in that it provides a chemical and mechanical feedback to its interstellar medium. But also, of course, it influences the life and the death of the star itself, with one concrete example that it affects the mass of the black hole after the star dies. Which here, as example, we show a figure from Belsinski et al., where we have here the resulting black hole mass after the evolution of a star with a certain initial mass. And if we assume the standard wind prescription, we get these masses of black holes, while if we reduce the mass loss, this could potentially create much higher black holes. So this is one concrete example of how mass loss can affect it. So we want to be able to describe such mass loss, and this mass loss arises from some radiation-driven outflow. And for the hot stars that I will be looking at, it's line-driven winds, and these cause very extended atmospheres and winds. So if we want to describe them in detail, we need non-LTE radiative transfer to model this interaction between the radiation and the matter. So for this, we turn to the one-dimensional code fast wind, which we'll use to construct our wind models. So important for these models is that we want to have them dynamically consistent, which means that this equation of motion here in the steady state spherically symmetric case needs to be satisfied. So what we get from the radiative transfer that inputs here is mainly this radiative acceleration. So in a small schematic on how these wind models are constructed, we need to start from some initial guess of the wind structure and the mass loss rates and solve the radiative transfer here. From here, we get the radiative acceleration that feeds back into the momentum equation. And this we need to solve iteratively to get a converged solution. And for this converged wind model, we then get an associated mass loss rate and velocity structure, and also, if we want, a synthetic spectrum. So this type of setup we can use to study the behavior of the mass loss rate over the Hertzsprung-Russell diagram. So we did this for a set of O stars already, and here I show a setup for a larger part of the HR diagram, where we have wind models covering the effective temperature, luminosity, and also this fake third dimension of the mass here, also for different metallicities. So from this setup, we then get these wind models and thus the mass loss rates for all of these points. And we can then study its behavior with for these fundamental stellar parameters. And then such prescription, such a recipe, depending on these parameters, we then can compare to, for example, observations. Here I show a set of observations of O stars, which are adjusted for the clumping in the wind, because this clumping can, of course, affect for certain diagnostics the mass loss rate you derive from them. So for more detail on these empirical mass loss rates, you can also look at the talks by Callum and by Sarah. But in general, you can see, well, there is of course a large scatter, but there seems to be quite a good agreement with the general trend and the general order of magnitude for these observations. What we can do as well is compare them to existing theoretical predictions, where I also again compare it to the rates by Vink et al., which are commonly used in evolution models. I show here a sequence of mass loss rates just for a constant luminosity and mass. And what we can, for example, see is that for the O stars, we have a certain reduction by an order of a factor 2 or 3. But maybe more striking is that we have a larger discrepancies at colder temperatures. And this is below the so-called bistability jump. And this is because iron 4 recombines to iron 3, which in the Vink models adds a sort an increase of the mass loss rate by approximately an order of magnitude. However, we do not find such an increase from our models. That's why we have a larger discrepancy here. And to go a bit further into detail on why we do not find it, we have computed additional models which are not self-consistent, but instead we try to drive a higher mass loss rate using then also not a consistent velocity structure, but a beta type velocity law. And then here we can see the result of this, where I plot just this gamma factor, which is g rad over your gravitational acceleration, compared to the other terms in the equation of motion. So in the case of a consistent solution, these lines should fall together. Another way of looking at it is that we compare the gamma that we get from the radiative transfer to the gamma that the model needs to drive this kind of wind. And what we see from here is that in our case, for this type of model, we lack the force that we need to drive an outflow through the sonic point of such a high mass loss rate. So in this case, our models, if we would then continue to solve them towards a consistent solution, it would favor the lower mass loss rates instead of these. So if we now look at how this impacts the stellar evolution, we have, I show here the evolutionary track of a 60 solar mass stars using the different mass pulse prescriptions. And I want to focus on two results here in this plot. One of them is that if we use our reduced massless weights in this solid line, we see that the star ends up on the cooler side of the HR diagram, and it does not have enough mass loss to strip its hydrogen-rich envelope to form what we call a Wolf-Rayet star. So we seem to have trouble creating Wolf-Rayet stars through a single star channel. Of course, these stars could also be stripped through binary interaction, but for a more empirical approach to this topic, I advise to look at Tomer's talk. Another thing we can see from such evolution calculations is that the final mass of the star before it dies is higher because less mass is lost from its envelope. And this could directly relate to the mass of the black hole that it leaves behind. So here I show a small figure of a study that I did together with a master's student, where I again show the final mass of the star or the resulting black hole compared to the initial mass of the model. So in this case, we look at the helium core mass of the star, which we then assume determines as which type of supernova it would explode. So, and if this mass stays below this line of which determines if it would explode as a disruptive type of parent stability supernova, it can instead directly collapse and adding its core mass and its envelope mass to form a high mass black hole. So what we saw in the Belczynski models, where there was an ad hoc reduction of the massless weight, here with our reduction, we find we could also reproduce potentially higher mass black holes. So in short, in summary, so we have computed detailed wind models to provide new mass loss predictions, which seem to be lower than the ones previously derived. And additionally, we do not find a bistability jump from our models. Additionally, when we look at them in the stellar revolution, we have trouble creating Wolf-Rayet stars, but we do seem to be able to create higher mass black holes. However, of course, we still need some mass loss across other parts of the HR diagram. We, for example, are missing the models at very high luminosity, which relates to the very massive stars. On the other hand, we could, there's also potential other ways of stripping the envelope to create Wolf-Rayet stars. I mentioned the binary channel, but of course, other things that are not yet implemented in evolution calculations are mass loss through eruptive type of event, or LBV mass loss. So this could potentially strip a single star to become a Wolf-Rayet star, even including our reduced massless weights. I thank you for your attention.
Thank you very much, Robin, for a nice talk and again being ahead of time. So I see there are a few questions. The first one by Alex Gomas. Alex, can you unmute? Yeah.
Okay, thanks, Robin. Very nice talk. Just a short question about the clamping factor of your fast wind models. Did you consider as a free parameter, or did you get some trend about the different value for massless rate or something like that?
Yes, so in this case, the clumping factor is actually not included in the models. And that indeed changes, for example, what synthetic spectra, how they would compare to real spectra. However, for the massless weight that we predict, it doesn't really have an influence, because often the clumping has an onset after the sonic point. And if we include this clumping, it does not seem to affect the massless weights we predict for these models.
Okay, thanks.
Okay, so next question by Yorick.
Nice talk, Robin.
Thanks.
Very surprised you don't find a bistability jump, but that's maybe, I need to think a bit more about that one.
Yes, we do.
About the lower massless rates for the O stars. Of course, the comparison you showed is for normal O stars, where, of course, the results depend on clumping and porosity and so on. And we have this model independent transition mass loss rate indicator where we know that the mass loss rate in the Monte Carlo rates is of at least of the correct order of magnitude. But if we extrapolate yours, then you have a factor 2 to 3 too low at a transition rate. But that's just an extrapolation. So have you done any calculations in that regime?
Sorry, which regime are you talking about?
I'm talking about the 80 solar mass stars, the very massive stars.
Yes,
so,
yes. So indeed, as I mentioned, so I guess our rates are not yet applicable for the very massive stars because we do not have the models there yet. So if they would be extrapolated, indeed, I guess our rates would be lower, but I'm not sure if we can just extrapolate to these higher masses. So we first should need to compute models that are able to model such massive stars before we can really say something about that.
Sure.
Okay, thank you. A third question by Andreas Sander. Andreas?
Yeah, thank you. Thank you very much, Robin, for a really nice talk. You showed that interesting temperature comparison plot. And I think one of the things, apart from the missing by stability jump, that immediately struck me is that you get this decreasing trend with temperature, with lower temperature, while the Wink recipe and also what you maybe would naively think due to the radius change, you would think that the mass loss rate goes up. So can you elaborate a bit on that, why you have such a different trend there with temperature?
Did you mean at the lower temperature end?
No, at the higher ones, when you start from 60,000 and then you increase in the Wink recipe, but you actually immediately have a decrease in the mass loss rate.
So our predictions are here on black. So we still increase our predictions. So we do not find this kind of downturn as is found in the Wink et al. Models. So even though, for the hotter stars, we still predict that the mass loss rate goes up when we increase the temperature at these fixed values. So that is sort of what we get as a best solution from our combined set of models.
Okay, yeah, it would be interesting to look at the precise atomic data, I guess, but that's a far more detailed discussion. Thank you.
Yes, thanks.
Okay, thank you, Robin, again. And we have to stop here. So thank you to all the speakers of the first session. So we will now take a short break and be back at 4:30 European time for the session 2. So thank you. See you in a few minutes.
So welcome back, everybody. I think we should start if we don't want to start too late and to finish too late. So the first speaker of this second session for the afternoon is Peter Blanchard, which will talk about us of evidence for magnetar powering and insights into the progenitor of superluminous supernovae. Please,
Okay,
Peter.
thank you. Okay. Hey, yeah, so my name is Peter Blanchard. I'm a postdoctoral fellow at Northwestern University. And so we'll just jump right in here. Okay. So like normal supernovae, superluminous supernovae can be divided into those that show hydrogen in their spectra and those that don't. So here I'm going to be focusing on the hydrogen poor stripped envelope superluminous supernovae, which generally have very blue hot spectra at early times with unusual absorption lines from oxygen. But then later, as time moves on and they evolve beyond peak, they evolve to look somewhat similar to normal stripped envelope supernovae, indicating a link between their progenitors. In addition, these events are about 10 to 100 times more luminous than normal supernovae. And so superluminous supernovae have significantly expanded our knowledge of the ways that massive stars end their lives. And so some of the key questions that this field has been trying to address are some relatively fundamental things like what powers their light curves and whether or not there are multiple power sources to explain the wide diversity that we see. And in addition, like all supernovae, we want to connect the explosions to the star that's actually exploding, the progenitor. So it's been shown that radioactive decay, the power source of normal stripped supernovae, is unable to explain the light curves of superluminous supernovae. Though parent stability explosions, which produce very large quantities of synthesized radioactive nickel, has been argued for several very slowly evolving events. So one of the alternative models that's been proposed is the circumstellar interaction model, where the kinetic energy of the expanding ejecta is converted into radiation through shock interaction with a circumstellar medium. But a significant problem with this model is that we don't see interaction signatures in their spectra. And in addition, X-ray and radio observations of large samples have indicated relatively low circumstellar densities. So one of the more popular alternative models is that of a central engine, and specifically the spin down of a rapidly rotating magnetar, where the ejecta is essentially heated from within through the conversion of rotational energy from the magnetar into radiation. And this model can explain both the light curves and the spectra. And some of the best evidence for magnetar powering comes from late time Hubble Space Telescope observations of a few superluminous supernovae that have revealed light curve flattening consistent with the power loss spin down of a magnetar. So in these two events, we see a considerable flattening at very late times to a decline rate much slower than that of the decay of cobalt-56. So this is really exciting because the late time slope and evolution are sensitive to the gamma ray opacity, which controls how the non-thermal radiation from the magnetar itself is thermalized and reprocessed into optical radiation. And so this opacity is related to the physical properties of the magnetar wind nebula. So this is an extremely promising way to probe the physical conditions in the innermost part of the explosion. In addition, the link between superluminous supernovae and other engine-powered transients like gamma ray bursts has also pointed us towards the central engine model. Both superluminous supernovae and GRBs occur in similar host galaxies, these low metallicity dwarf host galaxies. And also these superluminous supernovae are similar at very late phases in the nebular phase with that of the supernovae associated with GRBs, these type 1c broadline events. So the similarity of their nebular phase spectra indicates a similar ejecta composition and structure. So moreover, this magnetar model can explain the full diversity of light curve behavior that we see in superluminous supernovae, which span a very wide range of evolution timescales, and in particular, this late time flattening that we've seen in several events. And so this advent of very large samples that we've collected over a decade's worth of surveys is now enabling us to perform statistical studies to understand what the engine and ejecta parameters are of these systems. And so from this light curve modeling, we found that the required spin periods of these magnetars need to be roughly between 1 and 8 milliseconds, with magnetic fields of about 10 to the 13 to 10 to the 15 Gauss. And now we can also start asking questions about the stars that are producing these explosions from looking at the ejecta masses that we infer from this light curve modeling. So to accomplish this, I decided to investigate what we can learn about the stellar evolution processes that form the progenitors by studying the pre-explosion mass distribution. So we have this basic picture of the evolution of a stripped supernova progenitor. And so the idea here for this project was to take the observed pre-explosion mass distribution, which we get from the ejecta mass estimates from the light curves, combined with a nominal remnant neutron star mass, and then compare that with the predicted distributions from various stellar evolution models, which take into account single versus binary evolution, rotation, and metallicity, combined with an assumption about the initial mass function. So here I'm plotting the pre-explosion mass distribution inferred from the Bayesian light curve modeling of 62 events. So for each event, we have a posterior on the ejecta mass and the progenitor mass, which fully takes into account the uncertainties on that measurement. And then for all of these events, we combine it together into one final distribution, which is the black line shown here. So this distribution shows a broken power law shape between progenitor masses of about 4 and 40 solar masses with cutoffs at lower and high mass. And interestingly, this drop off at high masses occurs roughly at a core mass of about 40 solar masses, which is roughly the core mass that we expect the pulsational parent stability to start becoming important. So it's interesting that potentially this drop off that we see in the superluminous supernova distribution is an indication that for stars at higher masses, they're either directly collapsing to black holes or they're manifesting as different types of transients because of something like the pulsational parent stability. On the right here, I'm comparing the distribution with that for normal stripped supernovae, where we find that the distribution extends to much higher masses and generally exhibits a flatter shape over this mass range. And so this is indicating that these normal stripped supernovae and hydrogen porous superluminous supernovae are coming from a different sort of set of progenitors. So now that we have this observed distribution for superluminous supernovae, we can go ahead and compare it with the predictions from stellar evolution models, and in particular, models that span a wide range of masses. We actually have a predicted relationship between the initial mass and the core mass. So first I compare to single star models in the top left panel here, looking at both solar and low metallicities. So the cyan curve here is for solar metallicity, and because of the strong stellar winds, you essentially have a cutoff kind of in that distribution around 14 or so solar masses. So you're unable to explain the very high mass superluminous supernova progenitors.
Peter, you have 3 minutes left.
3 minutes, okay. And so looking at low metallicities, this dashed line here, we find that the core mass function for these metallicities generally can reproduce the overall shape of this distribution, but formally does not predict a broken power law shape, and is statistically inconsistent with the observed distribution. So importantly, these single star models that I'm comparing with, they don't take into account the rapid rotation that we expect is required to produce a magnetar. And in addition, these models predict that the final star will retain a significant fraction of its hydrogen envelope, making them incompatible with the stripped progenitors that we know are required from the spectra. So one way to lose mass at low metallicities and potentially to maintain the rapid rotation is through binary interactions. So the remaining panels here are comparing with stripped binary stars from the BPAS models, again, looking at various metallicities. And I find that the stripped binary distribution of final masses for metallicities of about 1/3 solar is best able to sort of reproduce this broken power law like structure in the distribution. And interestingly, this metallicity of about 1/3 solar is what we find from the host galaxies of superluminous supernovae. So importantly, although a given stellar evolution model, will have a prediction, that there are final stripped stars that might have high masses in the range of 10 to 40 solar masses, like some superluminous supernovae. Whether that star will actually explode is another question. And in particular, at those high masses, you need significantly larger kinetic energies than the canonical 10 to the 51 erg for normal supernovae. And so this extra kinetic energy might actually be possible if the magnetar is able to not only supply energy for radiative output, but also kinetic energy for the explosion. So it's possible that this broad nature of the superluminous supernova distribution is an indication that magnetars can enable more massive stars to explode. So finally, our large sample allows us to investigate correlations between the ejecta and engine parameters. So looking at mass versus initial spin, we find a correlation where events with lower masses are systematically at slower initial spins. And this is apparently a physical effect and is not explained by observational biases. So looking at the colored points in the background here, these are simulated magnetar-powered light curves. And we find that we should be able to detect events in this lower left-hand corner of parameter space with current surveys. And interestingly, this trend we find is roughly consistent with recent models of rapidly rotating massive stars that predict a similar trend due to varying amounts of angular momentum transport in the cores as a function of mass. So this observed distribution and this relationship we find is indicating that rapid rotation at low metallicity is likely a very significant factor that sets the progenitors of superluminous supernovae apart from those of normal stripped supernovae. And I'll just go ahead and leave the summary here and take questions.
Thank you, Peter, for stopping right in time. And this talk is now open for questions. Don't be shy. Don't see any hand raised. Are there questions on Slack? Ah, here we are. So Morgan, maybe first.
Hey Peter, thanks for the nice talk. So perhaps I missed this, but I was just wondering how you actually construct your sample of superluminous supernovae. Because I guess an observational survey, you're biased towards finding the brighter events at higher redshift. So is that a problem for doing this kind of statistical analysis?
Yeah, that's a great question. So I am considering superluminous supernovae from a variety of surveys, and you're right that some of them are from slightly higher redshifts than others. But I did look and see if there were any selection effects that would affect the mass distribution because of that exact reason, where you're at higher redshifts, you're going to be biased towards more luminous events. And it turns out that did not have any substantial effect on the mass distribution.
Okay,
But yeah, that's important, definitely important to consider for this kind of study.
And we will take the question of Flo Pro-Garden.
Yes, thanks, Peter. I was wondering, so is there, do you see any evidence that maybe they come from two, like that there's contributions from two populations, say both single and binary, for instance, or is, for instance, the last figure that you showed kind of showing like, oh, it might be just one? Thanks.
Yeah, I mean, I think it's definitely possible that, you know, there are multiple progenitor populations. You know, of course, you know, there's not just a population from one metallicity, you know, so there, you know, there could be, you know, a range of metallicities that enable a superluminous supernova progenitor to form, and potentially, you know, some fraction are single stars. I think that's something that we'll be able to address as we build up larger samples to look for more similar kinds of trends.
Sorry, Noam, but we have to move on to the next speaker. Could you maybe ask your question on Slack? Are you registered on Slack, Noam?
Yes, it's okay, fine.
Thank you. So we will move to our next speaker, who is Dominic Bowman. We'll talk about massive star interiors revealed by gravity wave astroseismology and high resolution spectroscopy.
Yes, thank you, Sylvia. And thank you to the organizers for giving me the opportunity. You should see some slides and you should hear me speaking.
Yes, we do.
Perfect. So I'm going to talk a little bit about some recent results that we've obtained based on astroseismology, so the study of variable stars amongst massive star populations, and how the combination of high resolution spectroscopy has also helped unlock some of the secrets of their variability. I'd like to highlight a few names as well, because this is, of course, not my own work. Simon, Matthias, and Maigane Pedersen, who if you're not aware of their papers, then please go have a look at them. They're doing fantastic things, I'm going to show you some of their recent and soon to be in the literature results. So when we talk about variability in the early type stars, there's three and a few other main classes. I'm going to talk to you about the ones that are on the screen now. So on this astroseismic HR diagram, starting from the intermediate mass stars, you have what's known as slowly pulsating B stars. And these have gravity mode pulsations of order a few days and masses between about 3 and 10 solar masses, thereabouts. You've probably heard of the beta Cephei pulsators, and so the lower limit being about 8 solar masses. Currently, we have stars that extend beyond about 25 solar masses that fit the beta Cephei class, but we really don't have an upper limit on beta Cephei stars. So these could be incredibly high mass stars. And then the third relatively new type of variability is what we used to call periodically variable supergiants, but I have convinced Peter Papich to remake his figure to call it stochastic low frequency variability. And this could have a potentially a range of mechanisms, but the period range of the variability is quite large. So it's from minutes up to several days, and it seems to be nearly ubiquitous in the photometry of OB type stars. When it comes to pulsations, there are two main types. So we have our gravity mode or buoyancy oscillations, with gravity being the restoring force. And we also have pressure oscillations, where the pressure force is the restoring force. And ideally, we want stars which have both gravity and pressure mode oscillations, because they are sensitive to different locations within a star. The gravity mode oscillations are very sensitive to the near core region. Specifically, that Brunt-Vasala frequency profile means their probing power just beyond the convective core of a main sequence early type star is very good. The pressure mode oscillations are more sensitive to the envelope of your favorite oscillating star. And so both together gives us the ability to probe physics as a function of radius within the star. A nice property of the gravity mode oscillations is that they are asymptotic in period. So as you evolve from the zero-age main sequence, just showing you a simple HR diagram here with a couple of what we call period spacing patterns, with each dot here representing the period of an individual gravity mode oscillation. As you evolve and the convective core will shrink in your early type star, it will leave a chemical gradient behind. And the gravity modes are very sensitive to glitches in any sort of profile within the star. And so as the star evolves, you get what we call dips or this structure in the period spacing pattern, which gives you a very tight constraint on the chemistry, but also specifically the convective core size in your main sequence phase. Of course, if you have different convective regions, so if you've got a hydrogen shell, the same logic really applies, but I'm focusing here mainly on the main sequence stars. And we analyze these stars using what's known as the traditional approximation for rotation, which allows us to not only extract the chemical mixing in the near core region, but also allows us to deal with rotation up to about 80% of the critical rotation, which covers a very wide parameter space. This is a grid of models which was calculated for about a 15 solar mass star, about halfway through the main sequence. And you can see here the different colors I've put as different fractions of the critical rotation here. And going from the top to the bottom, I have increased in the stellar evolution code that I used, which was MESA here, the amount of envelope mixing, which is increasing as you go down the plot. On the right-hand set of panels, I've increased the amount of convective core overshooting, which I've expressed here in the diffusive exponential representation here. So not only do we get a mass and an age from the astroseismology of G modes, we also get a constraint on the near core mixing and the envelope mixing. And there is some degeneracy between these, but we can effectively decouple them. So here's the first set of results that will be in the literature very soon. I can't tell you where, but you can probably guess from that statement. And this is a study that has been led by Maeve Ederson, who's now at KITP, who analyzed the first large sample of slowly pulsating B stars using astroseismology. 26 might not seem a very large number, but before Mai's paper, there was only 2. So this is a very large increase in the number of stars. And from different setups, so different representations of the physics that can possibly be included inside stellar evolution models, we have 8 different descriptions here. And you can see the different types of physics that we included. And essentially all of these different physical prescriptions are characterized by some of the parameters that you see here that you might be familiar with. So convective core overshooting, the core mass size, the mass of the star, age by proxy of the hydrogen content in the core, rotation, envelope mixing, and metallicity. And our premise, our forward seismic modeling strategy is that from your favorite space telescope, you collect a light curve, you're able to extract the individual pulsation mode frequencies of an oscillating star. Using their period spacing patterns, which I showed you on the previous slides, you can identify the geometry of the modes and effectively delimit the possible parameter space using parameters such as TEF and log-G to perform your seismic modeling. And what I mean by that is that you're finding the best model within a grid of evolution codes whose theoretical pulsation frequencies best match the observed pulsation frequencies. And so you can do this in various statistical frameworks, but Mai also in her paper, she looked at using statistical models in addition to the forward chi-squared modeling that people might be more familiar with. Well, what are the results? They're very interesting. Firstly, we find that most of these stars are pretty much rigid rotators, which means that the near core region and the envelope are rotating similarly. There's a little bit of discrepancy, but they're all pretty much within a few percent rigid rotators. And the more interesting aspect is that different types of physics seem to describe different stars differently. So there's a variety of structure in the mixing profiles in these slowly pulsating B stars. So I'm showing you a figure that will be in the literature soon here from Mai's paper, where the envelope, the overshoot, and the core sizes are denoted as a function of the coordinate in the stellar mass, with the Y denoting the total mixing coefficient. And there isn't anything incredibly strong to say from this figure, but there are correlations that are quite encouraging, such as correlations between the rotation of the star and the amount of mixing that we need in the envelope. But I will highlight also that some of the mixing coefficients that we need in these stars are actually quite low compared to what traditional rotational mixing would require for such a high rotation rate. So this is very interesting. Not one model fits all stars equally well, but that's a possibility to improve models. I won't spend too much time talking about the Beta Cephei stars, but if you are attending the European Astronomical Society meeting in a couple of weeks, my PhD student Seaman will present his analysis of what we're doing for the high mass pulsators. And he's identified some very nice new Beta Cephei stars that have been discovered using TESS. And you can see here his excellent grid of models, which we can perform the exact same philosophy with forward seismic modeling to extract the best fitting physics. If you want to see what's already been done for Beta Cephei stars, I also wrote a paper last year which tried to gather all of the different overshooting, the envelope mixing, the rotation rates of these pulsating stars and tried to put them in one place for future reference. So I'd encourage you to have a look at that paper if you've not already done so. Finally, I want to talk about the diverse variability that we're finding in massive stars. And this is, again, another hot topic that massive star research always seems to have. I'm very happy that the observations are making waves, and that is an intentional pun. But what we find in photometry of massive stars is this broad component of low frequency excess. 3 minutes left?
Yes.
There we go. Thanks. And we find that it seems to be nearly ubiquitous in the photometry. So I'm showing you observations of a 25 solar mass star near the ZAMS with its TESS-like curve on top and the amplitude spectrum on the bottom. And on the left, I'm showing you some hydro simulations of core convection, which includes part of the radiative envelope here. And you can see the beautiful waves that are excited in this envelope region. And if you do a comparative study, we find a pretty good qualitative, and emphasize that word, qualitative comparison between the waves generated from core convection and the surface variability that we find. We're going to hear a little bit more about this in William's talk, I think, on Friday. But I should also mention that things like surface convection and also the winds in massive stars are also important. But core convection seems to be quite an encouraging, non-mutually exclusive phenomena to try and explain observations with. And the reason we think that's true is because when we look at a large sample of massive stars covering a range of masses, ages, and more specifically metallicities, we don't seem to find any dependence on the metallicity of the star and the morphology of this low frequency noise component, this gravity wave signature. We do, however, find that for brighter stars, so here is a function of the amplitude of the variability as a function of the brightness, the frequency, dominant frequency range decreases as you go to brighter stars, but there's no dependence on the metallicity in the profile that we see here. We can go one step further. We look at this using spectroscopy. And so earlier, well, not earlier this year, last year, we had a look at combining Jakob spectroscopy with TESS photometry. And we find this beautiful correlation where if you go to more massive or more evolved stars, the amplitude of the frequency variability increases and the frequency of that low frequency variability decreases. So the waves, the variability, whatever they are, they seem to be probing the evolutionary properties of the star very nicely. And this makes perfect sense for waves because waves are constrained by the Brunt-Vasala frequency profile of your star. And so as you go to later ages, more massive stars, the waves will be tracked to a different frequency regime. This also nicely correlates with the amount of macroturbulence, that spectroscopic broadening parameter that you need in massive stars. And so here I'm showing you how that for larger amplitude stochastic variability, you also tend to see larger macroturbulence. And of course, correlation doesn't mean causation, but it seems to be that the physical mechanism causing macroturbulence and the stochastic variability seems to be quite well correlated. And I also highlight the numbers on this y-axis scale here. Sometimes in these O stars, we need hundreds of kilometers per second. So any mechanism that explains this variability needs to be able to predict such large values of macroturbulence, large values in the photometric variability, as well as the evolutionary properties that seem to be largely metallicity independent. So that brings me to my conclusions. Astroseismology is providing interior properties for a range of masses from about 3 up to upwards of 30 solar masses. We can do this for a broad range of rotation rates. We find that there is a broad range in the overshooting derived from gravity modes and also a broad range in the envelope mixing. We're moving beyond astroseismology of coherent modes to more of astroseismology of traveling waves. which we believe explain the stochastic frequency variability we see in nearly all of these stars. And if you want to know more about these consortia, you can just message me on Slack, because of course this is a collaborative effort. So thank you very much for your attention. I'm very happy to take questions.
Thank you, Dominique, for this talk, which is open for question, and there is already one by Matteo, please.
Hi, Dominic. Thanks so much for this talk. This is a very cool results, especially the SPB stars. I wasn't aware of it. Very much looking forward to read the paper. Just wanted to follow up on the discussion about metallicity effects in the red noise observation in massive stars. If you go back to your plot where you're showing the LMC sample, yeah, here. So your argument is that going to looking at LMC, you don't seem to see a difference in the observed stochastic low frequency variability. However, my question for you is that when you look at LMC, you naturally have to look at more massive stars. And you can actually see that your LMC sample has higher values of SLF, if you look in your first plot, which shows that probably you're looking at more massive stars. So I'm wondering if your metallicity effect is actually offset by the fact that you're looking at more luminous objects.
Yeah, so that's a great point. So the caveat of this plot on the left is this is a Gaia color magnitude diagram for which the uncertainties on reddening and extinction do mean that the location of these stars is kind of weird. So I won't promise that these are all massive or low mass stars because of that. That's why we need the spectroscopy. But the encouraging thing, I think, from these results, what we're showing here is that some of the initial spectroscopy of those LMC objects do imply that they cover a range of masses. And so I still think that the metallicity independence is an important result from this, but that should be confirmed from spectroscopy. And that's what, together with Sergio Simon Diaz, for example, we're starting to look at. The point of the metallicity independence is that the gamma value that I'm quoting here in this function essentially sets the gradient of the slope here. And so for different convective regions, the efficiency of the convection will naturally scale with the metallicity. So I totally appreciate your point saying that in the more massive regime, yes, maybe we're seeing more luminous stars, but we definitely do have stars that are below that sort of 5 solar mass boundary that still have the stochastic low frequency variability at the LMC metallicity. So this has sort of led me to think that maybe we're seeing multiple mechanisms simultaneously. And the question really is, in which part of the HR diagram does one mechanism dominate?
Gloria, is your question very, very quick?
Hopefully. I was just wondering, you reached the conclusion of rigid rotators, and I was wondering if this is independent of the rotation, the measured rotation velocity. And of course, the second question would have to do with the uncertainties in this conclusion that these stars are rotating as rigid rotators. This may take longer, and you can put the answer in the Slack if it does. Thank you.
Well, I'll just leave this on, so please don't distribute the results, but you can have a look at this just very quickly. This is the correlation plots for various things. So if we're looking at, I now need to find it, where's rotation? Rotation color-coded as a function of whatever parameter you want on the top two here, for example. So we do find correlations between different parameters, but the rigid rotation does seem to be for the slowest rotators and the fastest rotators. So we need a very efficient angular momentum transport mechanism operating inside stars. And I should also comment that's for young stars and old stars. They all seem to be rigid. So whatever it is, it's extremely efficient.
Thank you.
Thank you, Dominique. And now we move on to our next speaker, who will be Ricardo Dorda, who will talk about the binary fraction of the cool supergiants in the Magellanic Clouds.
Hello. Thank you. Are you, sorry. Are you watching my screen now?
Yes, we do.
Yeah, thank you. Good afternoon. Thank you to the organization for this opportunity. Today I'm going to speak about binaries among high mass stars, and this is a very hot topic, very important topic, because as many experts have demonstrated, most massive stars are binaries, and most of them are going to interact with their companions during their lifetimes. These interactions are going to determine the subsequent evolution of the stars, affecting to their evolutionary paths in a critical way. Also, they are going to affect to so many high mass stars that the aspect of the appearance of the clusters is going to be affected by the binarity among high mass stars. And finally, binary systems among high mass stars are going to be the progenitors of the compact object systems, which are going to be the progenitors of the gravitational waves. In short, the effect of the binarity among high mass stars is key to understand their lives and deaths. However, most of the studies in this topic have been focused on the OB stars, and only a few studies have focused attention on the evolved massive stars, the cool supergiants. And these stars are important because they are at the end of their lives. So the number of binaries among these stars are testing the predictions done by the evolutionary models built on the observations of OB stars. The previous works are not so many. In the 80s, Barkey and Mayor found 180 cool supergiants in the Milky Way, which they studied this number of cool supergiants by measuring their radial velocities in different epochs. Also, using this multi-epoch radial velocity method, Patrick et al. Studied recently a small number of cool supergiants in 2 regions of the Magellanic Clouds. On the other hand, Nugent et al. Have studied the presence of companions in cool supergiants by searching in the blue far of their spectra, looking for blue features of blue stars present in cool supergiant spectra. They found a number of cool supergiants with these signs of blue stars there, and they used these stars to train a machine learning algorithm, and by using also the photometry. And through this photometry, they have studied a large number of cool supergiants in the Magellanic Clouds and also in other galaxies. In this work, we decided to study this topic by using the radial velocity variations of cool supergiants. And this is not an easy technique for these stars because due to the very large size of these stars, their minimum periods are extremely large, about several years or even decades. So we needed data from as far in the time as possible. So we collected all the catalogs of cool supergiants with radial velocity data available for us. We collected in total data for more than 1,000 cool supergiants in the clouds. We used 6 catalogs and focused on cool supergiants, and also 2 generic catalogs, Raya and Rave, which provide radial velocities for many of our cool supergiants. In total, we have 9 epochs from the 80s to the 2016. The main problem of using different catalogs to compare radial velocities is the possibility of systematic errors. And to correct them, to correct these catalogs of such effects, we cross-match all the cool supergiants in each catalog with their Gaia counterparts, and we calculated the corresponding differences. As I saw here in the first histogram, we found small differences, because if there is no systematic effect between catalogs, we shall see all of them centered with an average of 0. So we used the median, the median difference between the radial velocities and the Gaia radial velocities to correct each catalog to the same radial velocity frame, as you can see here in the second histogram. Now, once we have all the data, all the radial velocities in the same frame, we can compare different epochs from different catalogs. And to detect binaries, we need to fulfill 2 different criteria. Firstly, the radial velocity variation has to be large enough to be caused by an orbital movement, because cool supergiants have large intrinsic variations, which are about several kilometers per second, up to 10 kilometers per second, it has been observed. And the second condition is that these variations have to be significantly, statistically significant, given the corresponding errors. So for determining which is going to be our limit, the radial velocity limit, we decided to plot the maximum radial velocity difference of each cool supergiant and plot an accumulated diagram here with the maximum radial velocity differences observed for each cool supergiant in our sample. And as can be seen, we found that this distribution has 2 very different slopes. One is below 11 kilometers per second, and the other is for stars with differences larger than 11 kilometers per second. And we think that this inflection point is due to because below 11 kilometers per second, we are dominated by the radial velocity variations from the star, the intrinsic radial velocity variations. Above this value, which matches with the observations of 10 kilometers per second, we are just seeing the radial velocity differences due to orbital movements. In total, by using this criteria, we found 22 cool supergiant 22 binaries in the LMC sample and 23 in the SMC sample. However, these numbers are not enough by themselves to determine the binarity fraction, because there is a number of biases in this work, and the main of those is the small number of epochs we have. Because as we can see here in this diagram, the dashed line shows how many cool supergiants we have with a given number of epochs. As you can see, most of our cool supergiants have 2 or 3 epochs only. And with 2 or 3 epochs only, it's very hard to find radial velocity differences. Significantly large, I mean. So here in the other line, the solid line, you can see the fraction of these cool supergiants for which we have found variations above 11 kilometers per second. As you can see, this number is low this fraction is low for those stars with 2 or 3 epochs, but it escalates to higher numbers when we can have more epochs. The problem here is, if we only take those cool supergiants with more epochs for the calculation, then our error will be very large, because the error depends on the number of stars available for the calculation of the binarity fraction.
So we decided have 3 minutes left.
Thank you. We decided to find a balance between both terms, and we took the cool supergiants with 5 or more epochs in the LMC, the cool supergiants with 6 or more epochs in the SMC, because with those numbers we get an error of 5% or lower. With this, we didn't apply any other correction, because we didn't want to use any assumption about the distribution of periods or masses or anything, because this data usually depends on models or on observations of OB stars. So we wanted to provide a lower limit for the binary diffraction among cool supergiants, which will be independent of any other consideration. And we found that for both galaxies, the SMC and the LMC, a very similar value, 15% of the cool supergiants in both galaxies should be binaries. By comparing these results with other works, we can see in one side that if we compare with the radial velocity studies, our data is compatible, and also with the values obtained through photometry and machine learning algorithms. On the other hand, we found a difference with the method of just checking if the cool supergiants have a blue component in their spectra. This can be due to several reasons. For example, they didn't use samples specifically designed to find cool supergiants with blue components. They just check on already observed cool supergiants. And actually, we went to our sample and we checked in how many of the cool supergiants in our sample we can see these blue star features. And we found that it is 4.6%, which is completely compatible with that they found. In conclusion, we think that we are providing a very reliable binary diffraction, lower limit for the binary diffraction of cool supergiants. And given the metallicity differences between SMC and LMC, we think that this limit can be applied to any cool supergiant even in the galaxy. And just to end, we are still working on this. We are collecting more epochs through large catalogs, but also we are doing our own observations to have more epochs for our sample. With this, we expect to increase the number of cool supergiants, binary cool supergiants. And finally, we are using also ultraviolet photometry and the radial velocity variations observed to characterize the companions of these cool supergiants, which will be the next step in our work. So thank you very much for your attention.
Thank you, Ricardo. Are there any questions for Ricardo? Roberta, do you want to ask yourself your question? You write it in the chat.
Is it in the chat?
There is a question. Oh, yeah. So Roberta is asking, what when you say cool supergiants, is this a mix of yellow and red? What are the spectral types of your binary candidates?
The spectral types are from G to M, because in the Magellanic Clouds, due to the metallicity effects, there are many cool supergiants. There are red supergiants with K and M types, but also, especially in the SMC, a large part of the population are G type. And
she's asking also if you check those with large velocity variation with light variability.
We check a few cases and we didn't find a clear correlation. We checked only those with 11 kilometers per second or higher, but we didn't see anything important. Not a clear correlation between the both terms.
Okay, we have a question by Tomer also.
Yes, hi, thank you very much. Maybe I misunderstood something, but you showed at a certain point plot showing the binary fraction as a function of this delta V max. And what I didn't understand is why this fraction doesn't go to 100% when delta V max goes to 0. Why does it converge to 35% or so?
The percent. Here. Do you mean in 8 epochs?
Not this one. No, it was in a previous slide.
Okay.
Here. Yeah.
Yes, because this is because of the second condition. We are discarding all the variations which are not statistically significant given our errors. So here we can see a second line marking the point where we think that the differences are so small that they cannot be considered statistically significant.
Okay, I understand. Thank you.
Welcome.
Thank you, Ricardo. We will move now to Eowyn Farrell's talk. So he will be talking about connections between internal and surface properties of massive stars at different evolutionary stages and the uncertain masses of SN progenitors.
Great. Hi, everyone. My name's Eowyn Farrell, and I'm a PhD student in Trinity College, Dublin in Ireland under the supervision of Jose Gros. And I've also been lucky to collaborate in this work with the researchers listed here from Trinity, Geneva, and Auckland. So I'd like to talk today about how to infer internal properties of stars from observations of surface properties. And I'll introduce a new technique which we call snapshot models and discuss applications of this technique to two areas, to red supergiants and strip stars. Being able to accurately infer internal properties of stars from observations of the surface properties is extremely important in a wide variety of contexts. And there are many different methods to make these inferences. For example, to determine the mass of a star from its luminosity and effective temperature, a common method is to plot a track from a stellar evolution model and the observations in the Hertzsprung diagram and compare the two. And for some applications, this can be quite a useful technique. However, there can be several problems with it as well. For example, the mass that you derive can depend quite a bit on the assumptions in the model related to convective overshooting, rotation, mass loss. It can be difficult to quantify the uncertainties on the mass estimate or degeneracies that might exist. And in addition, the wide variety of possibilities associated with binary interaction can complicate the problem. So in this talk, I'm going to focus on connecting internal and surface properties in applications to these two specific topics, but the technique that I'll discuss can be applied to a wide variety of research questions. So the two applications, as I said, are red supergiants, which are located here in the HR diagram, and strip stars, which are located across this approximate region. And just to provide some perspective on how stars reach these regions, over plot here the evolutionary track of a 12 solar mass single star in black and the same star in a close binary system in gray. And we can see here that the single star dies as a red supergiant, and the star in the binary system dies as a strip star. So these topics are connected to many areas of research, including red supergiant mass loss rates, the final fate of red supergiants, effects of binary interaction, ionizing photon emission, progenitors of type 2b and 2l supernovae, and the mass functions of neutron stars and black holes. And in all of these research areas, it's really useful to be able to determine properties such as the mass, core mass, evolutionary state, and so on. So to complement stellar evolution models, we've been developing a technique which we call snapshot models. So a snapshot model is a stellar structure model in hydrostatic and thermal equilibrium, as indicated by the sketch here. And they are a snapshot at a particular moment in time during the evolution. So they're not evolving in time. And the idea behind the technique is to compute a grid of snapshot models in which one internal property changes at a time. For example, we could compute a series of models with the exact same core abundance and core mass, but just changing the envelope mass, which might look like this sketch. And a key advantage of the snapshot models is that they allow us to systematically isolate the effect of one internal property at a time. And so in this case, it's the envelope mass. I'll briefly discuss how we compute these snapshot models in practice, but we'll be happy to go into more detail with anyone who's interested later. The first step is to compute a normal stellar evolution model. And we're working with the MESA code, but this could in principle be done with any code. And the exact choices for inputs regarding convective overshooting, rotation, mass loss are actually not too important. And this is because the purpose of this step is to generate a starting stellar model that will then modify. So the next step is to modify the internal structure in the desired way, which can be done in a few different ways. For example, by adding or removing mass to the model, or by changing the abundance profile directly by hand. So this is done to a particular stellar structure model that's taken from the evolution model at a particular moment in time. And then finally, we allow the model to relax to thermal equilibrium. And this step actually raises the caveat that some of the results apply only to stars in thermal equilibrium, although we can also perform further steps to account for stars out of equilibrium. So what does a grid of snapshot models actually look like? Well, here, for example, we have a grid of models during core helium burning all with the same central helium abundance of 0.5, and with a systematic variation of the core and envelope masses, as you can see indicated in this parameter space grid. And you can imagine that this allows us to isolate the effect of the core and envelope mass on the surface properties, and also on the internal structure of the star. So that's the snapshot model. So how can they be applied? How does it look in practice? So let's look at a grid of snapshot models at the pre-supernova stage. So they're plotted here in the HR diagram. On the left is a series of models with the same core mass of 4.3 solar masses, and envelope mass varying from 0 here on the left up to 25 solar masses on the right. And in the right-hand panel, the total mass is plotted as a function of effective temperature for the same set of models. So the first thing to note here is that as the envelope mass increases, the luminosity remains constant. And the second thing to note is that over a very wide range of final masses, from about 5 to about 30 solar masses, the luminosity and effective temperature vary very, very little. Here in the HR diagram. And this variation is much smaller than the typical observational uncertainty of supernova progenitors, which means that by using the luminosity and effective temperature alone, any individual determination of the final mass of a red supergiant is degenerate. Which is our first key result. So we repeated the same exercise for a range of different core masses, and this range covers the vast majority of core collapse supernova progenitors. And we do find the same result then over a large range of core masses. And the advantage of systematically constructing snapshot models in this way is that we can accurately map from a given observed region in the HR diagram to a range of allowed core and envelope masses, and also to quantify the degeneracies that exist. And we can compare these models then to archival images of supernova progenitors. So based on this grid of models that I just showed, we produced a relationship between the final luminosity of a red supergiant or strip star and its final helium core mass. That is independent of the typical uncertainties in a stellar evolution model. And so we produced this so this is our second key result, and we're able to produce this equation which can map from a given observed luminosity to the final helium core mass. Using this core mass luminosity relationship and the degeneracy discussed earlier, we're able to infer the core mass and allowed range of total final masses for directly imaged supernova progenitors based on the luminosity and effective temperature alone. So I included 2 examples here, but you can see in the paper for the full table. So we have one example of a type 2p progenitor, which is a red supergiant. You can see we're able to relatively well constrain the core mass. However, the total final mass could range from 3.3 up to 14 solar masses. And we also have this one example of this interesting event, which seems to be direct collapse of a red supergiant to a black hole, which again, we see similar results. So the masses are crucial for understanding how the star gets to that point and its evolutionary history. And what we're finding here is that based on its luminosity and temperature alone, the mass may be quite low or quite high. However, the core mass is quite well determined.
About 3 minutes left.
Great. So while I won't discuss in detail here, we do find similar results for red supergiants throughout earlier burning phases, with slight differences that change as a function of evolutionary state, which are interesting in other ways. And this has implications for masses and core masses of all red supergiants, including, for example, Betelgeuse. And the details are in the paper, again, so I won't go into them right here. And so let's apply our snapshot models to a different region of the HR diagram, the strip stars. So as a reminder, these can be reduced following Roche-Schlab overflow in close binary systems. So we computed a grid of snapshot models halfway through core helium burning. And this figure on the right shows in this first panel shows the envelope mass that corresponds to a given location in the HR diagram. And then this figure is the same, but for the core mass. And so we can apply this to observations. We applied this to an observation of a known strip star in a close binary system, HD 45166, and we can derive a core mass and an envelope mass that are consistent with its luminosity and effective temperature. And we can also apply the same technique using the pre-supernova models to a strip star progenitor of a type 2b supernova and determine its core mass and envelope mass. So the key result here is that we don't see the degeneracy that we saw for red supergiants for these strip stars, and the core and envelope masses are very well determined by the location in the HR diagram. So there are two key takeaways that I'd like to leave you with. The first is that the snapshot models are a useful tool to combine with the other tools that are out there to help to infer internal properties from surface properties. And secondly, while the mass determination based on luminosity and temperature alone is very degenerate for red supergiants, the core and envelope masses of strip stars can be well determined. So thanks, and I'll take any questions.
Thank you, Erwin. So we have a question by Dominic.
Hi, Owen. That's a really great talk. Thanks very much. Can you perhaps describe how you deal with overshooting in your models? Because convective core overshoot is degenerate with location in the HR diagram. So how do you deal with that?
Yeah. So we effectively consider the models in terms of the structural parameters that are a consequence of the processes like overshooting, rotation, and so on, rather than directly from the processes itself. So there might be different combinations of those processes or binary interaction that results in a core mass of, say, 4 solar masses. But that's kind of whatever way you get there, you still end up with that model as long as it's in thermal equilibrium. So it doesn't really matter. Yeah. Does that make sense?
No, that does. Maybe a quick follow-up. So what if you could put it in an alpha OV value, what would be the maximum that you're considering within that method?
Well, I guess the strip star models go all the way to just a helium star. So whatever that would mean, like full mixing of the star. Like we have models ranging like from core mass ratio of 1 all the way down to smaller than you would expect for single stars.
Okay, that's really good. Thanks very much. This is great.
Thank you, Erwin. I think there are no more questions, so we can move to the last speaker of today. And it is Emma Beezer, who will talk about the age of Westerlund 1 revisited. Emma, can you share your screen? Yes.
I will just do it now.
Perfect. We see it.
There we go. Cool. Thank you so much for inviting me to give this talk. I'll be talking about Westerlund 1 and I'll just dive right into it. So Westerlund 1 is a really interesting cluster in the Milky Way. It's highly extinguished. It was first discovered in the 60s, but because it is so extinguished, it's been really difficult to follow up. But it's thought to be an example of a starburst cluster, but one where we can see everything within it, so you can resolve all of the individual stars, whereas starburst clusters normally look more like this. These are some high redshift examples of starburst galaxies. So to study things like this, you need to have evolutionary models, and at the moment, the only thing that they can be calibrated against is a starburst cluster like Westerlin 1. So Westerlin 1 is also really interesting because it contains a lot of stellar diversity. So there's a whole host of massive stars that you might not expect to be coexisting all at the same time. So there's blue supergiants, Wolf-Rayets, there's 4 red supergiants, 6 yellow supergiants, an LBV and a magnetar. So there's really a lot going on. And all of this, so there's like literally no other cluster like this. And this means that Westerlin 1 is kind of seen as a bit of a Rosetta Stone type object, where you can sort of join the dots and say, oh, this is how long we expect each star to spend in each phase. But according to the single star model, for all of these objects to coexist together, there's only a really, really narrow range of ages where this can happen. And that age comes out at being about 5 megayears, because any younger than this and the cool supergiants wouldn't have had time to form, and any older than this, and you'd have expected all of the Wolf-Rayets to already explode. And this puts the progenitor population mass at about 30 solar masses. And if you extrapolate this, then the total mass of the cluster would be about 10 to the 5 solar masses, which would make Westerlin 1 the most massive galactic cluster yet discovered. And so if the progenitors are 30 solar masses, we can also have a prediction of how bright all of the stars, in particular the red supergiant, should be. So if the progenitor masses are 30, then you'd expect the red supergiants to be around here. So a 30 solar mass star, the red supergiant should correspond to a luminosity of around 5.5, which is right at the upper limit for where cool supergiant luminosities can be. That's right at the Humphreys-Davidson limit. So to get luminosities for the red supergiants, it's a little easier than doing it for the Wolf-Rayets, because a lot of the flux for the Wolf-Rayets comes out in the UV, whereas for the red supergiants, we should technically be able to get good luminosities from them by using their SEDs. But until now, a lot of the data in the mid-infrared, where these stars emit a lot of their light, has been quite saturated. So it's not been possible to get luminosities for these objects. But we managed to get Sophia data. So using Sophia forecast, we observed Westerlin 1. So here's our images here. So we observed in 4 wavebands from 5 microns out to 31 microns. And you can see in the plot on the right, the 4 red supergiants kind of lie in a straight line down the middle. So with this data, we complement it with archival data from Gaia and 2MASS. And for the red supergiants and the yellow supergiants, we end up with pretty much complete SEDs, as I'm showing here. So you can see the Sophia photometry is that marked with the crosses, and you can see it covers like quite a crucial wavelength range for the red supergiants. And when we have pretty much complete SEDs like this, we have a good technique to get reliable luminosities out. We don't need to rely on using bolometric corrections. We can simply correct the data for extinction and distance, and then integrate under the complete SED and end up with quite a reliable bolometric luminosity. And then we also have an updated distance for Westerlin 1 from Gaia DR3. If you're interested in the method, we've got a previous distance from Gaia DR2, but the distance comes out at this time about 4 kiloparsecs with pretty big errors on it. So we did this for all of the cool supergiants, so all 4 of the red supergiants and all 6 of the yellow supergiants, and we were able to update the HR diagram for Westerlin 1. So on this plot, I show the HR diagram with mist models plotted in the background showing the different ages. So the triangles on the left are all of the Wolf-Rayet objects, which I think come from a Crowther paper. And then we have the LBV with the pink stars. And then just by looking at this, you can see that the red and the yellow supergiants are much fainter than what you might expect for a 5 megayear cluster. So if I overplot a 5 megayear ice-core in there, you can see that they're all far too faint, clearly inconsistent with an age of 5 megayears. And just by eye, looking at it, it does look like they lie kind of more around the 10, 11 mega year mark, which is, of course, like double the age that's expected from previous studies trying to match up the cool and the hot populations. So there's clearly something going on there. So following this, we can also do a formal fit to the age. So using the least luminous red supergiant method, we're able to get a formal fit on the cluster age, and that age here, so you can see the PDF strongly peaks at 10 mega years, plus minus about 1. And with this, we also show the red dashed line is 6 mega years, and we can exclude ages of less than 6 mega years at the 99.9% confidence level using the cool supergiants. So this is obviously causing quite a bit of tension with previous age estimates. So we had a look at, can other things sort of reconcile this? So first of all, we considered binary models. So in this plot, I show BPAS populations for a 5 mega year and a 10 mega year population. So in the plot on the left, we have the 5 mega year population, and you can see that it does a pretty good job of matching the Wolf-Rayet. They're sort of the right luminosities coming out from that 5 mega year model, but the little green dot on the right of that shows that the luminosities of the cool supergiants still over predicted. So a 5 mega year model with even with binaries doesn't seem to make sense. And then in the plot on the right, we have the same thing again, but a 10 mega year population this time. And looking at it by eye, you can sort of see that it does still kind of match the Wolf-Rayet. There's only really one that's kind of too bright for it. And then on the right, we have the cool supergiants again. And you can see that it does a much better job of matching their luminosities. But we do know that neither model managed to recreate the number of yellow supergiants that we see in Westerlin 1. So there are also previous age estimates for the cluster from other methods, and one which has been done quite a lot is using the pre-main sequence stars to get an age out. And there's a few papers that have done this, so I've got them in the purple box down there, and also the Kudryavtseva et al. 2012 paper. And they all seem to come out at an age of about 5 mega years from the from simply fitting ice cranes to the pre-main sequence. They all come out again around 5 mega years. So we repeated this, but we used the updated extinction law from Daminelli, and the age increased from 5 mega years to around 7 mega years, but with pretty big errors on it. And that's not including the systematics from the error on the distance and the error on the extinction, which could all push the age up as well. But I just want to highlight from this how difficult it is to actually get a reliable age out from the pre-main sequence. So very few areas of the ice cranes actually have much weight when it comes to determining an age. So everything fainter than 15.5 here is consistent with any age less than 20 mega years. So there's very little diagnostic power there. And then anything brighter than 14.5 here has no diagnostic power either, because the pre-main sequence is always too faint, except for models that are less than 3 mega years. Which
Emma, you have 3 minutes left, sorry.
Cool, thank you. So it's always fainter than the models, except when the models are less than 3 mega years, which obviously doesn't make sense with the red supergiants and the yellow supergiants. So actually determining age from the pre-main sequence sort of depends on these two stars here, which we've termed the bridge stars in our paper. And even if one of these stars is, for example, an unresolved binary or sat behind extra foreground extinction that's not taken into account, then this will all this could all pull the age up, but basically everything hinges on these two stars. So it's actually really difficult to get an age out with the pre-main sequence. So another method used to determine ages is using eclipsing binaries, and Westerlin 1 has, I think, a few systems of eclipsing binaries in, and one in particular, W13, has quite a massive component. So the way you can work an age out from this is you use the radial velocity and photometric light curves, and you can get a dynamical mass for each object in the binary system. So then you can work out an age for the cluster by assuming the lifetime of the most massive component. And this eclipsing binary W13, it's had its mass determined 2 times, and both times the most massive component comes out around 33 solar masses, which also suggests an age of 5 megayears. So this is sort of the only tension that we can't really reconcile with the cool supergiants. We still get a really young age from the eclipsing binary. So this is where we need to put Westland 1 into context to try and understand what's going on with it. So Westland 1, if it is around 10 megayears, then maybe it's just that models can't match a 10 megayear cluster, but we see another cluster, RSGC1, which is around the same age. And the ages for this cluster are also based on the red supergiants, but the models do seem to be able to make sense of it. So RSGC1 has a large number of red supergiants, but it doesn't contain this really bright young population that we see in Westland 1. I think it's only got 1 blue supergiant in it or something. So the models can make sense of clusters this age. And another good analog maybe for Westland 1 is the R136 region, which is a young massive cluster in the association in the LMC, where there are cool supergiants, again, living simultaneously with hot massive stars. And in the Schneider paper, they suggested that there's an age spread here of 5 megayears in the age spread from the hot stars within the core. So it's possible that Westland 1 is also maybe having maybe experienced an extended starburst over a few megayears. It kind of makes a bit more sense with R136 because it's so much more massive than Westland 1, but this would reconcile the cool and the hot stars. So we favor the theory that Westland 1 is the product of a sustained starburst. And in this case, the red supergiants define the older limit of 10 megayears, and W13, the eclipsing binary system, sets the lower limit of 5 megayears. So given that there's this huge age spread, we'd recommend against using Westland 1 as a benchmark object. So thank you for listening. I'll take any questions.
Thank you, Emma. Thank you very much. There is immediately a question by Paul Crowther.
Hi, Emma. Yeah, just a couple of things. So I completely agree that well, certainly the 5 million year age that you would get from, let's say, the Wolf-Rayet has historically been almost certainly underestimated, because of course that tends to use single models, and it's well known that most, if not all, of the Wolf-Rayet stars in Westland 1 are binaries, and therefore the ages you would get from a binary model would imply probably maybe 7 or 8, maybe not quite as much as 10, but maybe more like 7 or 8 million years, because the numbers you've shown there were based on sort of a very rough approximation in terms of the parameters for Wolf-Rayet stars. So a more sophisticated job would probably imply something more like 7 or 8, maybe not 10 though. And then just a brief comment on the R136 NGC 2070 comparison. I mean, again, we want to be comparing like with like, and I would say the R136 cluster, central cluster, is a very compact region, very young. Whereas the NGC 2070 region is clearly a much more extended, over tens of parsec region, which is clearly has undergoing a, more like a continuous star formation over a range of ages. Therefore, you are sampling with supergiants in that. But I would say that there's no evidence for any stars older than a couple of million years within the central parsec of the region. So, so I would distinguish between the R136 cluster and the NGC 2070 region, and that is not a cluster because its scale is tens of parsec.
Yeah, so the scale is definitely like the thing that kind of makes it harder to reconcile. But if Westland 1 has undergone like a sort of extended star formation, then that would make it all make sense, right? But yeah.
Great, thanks.
We'll just take a last question by Francisco Najaro. And I suggest that all the others put their question on Slack, because we need to move to a discussion then.
Hi, Mark.
So Paco.
Yeah, great talk. I was wondering how much your results depend on the assuming the extinction law by Daminelli, especially in the around the J band and the I band, where your maximum flux will happen depending on the extinction law you apply. And then you have also two clusters at the galactic center. I mean, the one in the central cluster, which has a red supergiant and stars very likely or very similar to the ones the Wolf Rayets we see in Westerlund, and then the age is like Paul said, more likely about 5 to 7 or something like that, but not 10. So what is could be that the extension you're using is just forcing this larger age.
So we did initially do everything with Daminelli, but then we went back and we did it all again with I think 4 different extinction laws in the end, and it was never enough to make any significant age difference. I don't even think the best fit age really changed. Like maybe the errors on the best fit age changed a bit, but it doesn't look like extinction can pull the age down.
Okay, so now we will move to the discussion, which will be chaired by Jorik. And Jörg, do you have access to Slack? Can you ask your question on Slack? If you don't mind.
I will do.
Thank you. So Jorik, I
Yeah,
give you the
thank
floor.
you, Sylvia, and thanks to all the speakers today. I think that was very interesting. A wide variety of topics already. The reason for that, of course, is that we did things alphabetically instead of by topic. And there's a purpose for that, because then we can have some discussions perhaps that connect different things. Now it's a bit difficult to connect all the topics of today. So let me see if I can share screen. How does that work? Surely there's a share somewhere.
No pressure, Jorik. You only been doing that for years, so
yeah,
you still need time to work out the details.
It's okay. Maybe that was the Skype. It doesn't matter. I didn't have much on it anyway. So because Bestenijner and Björklund both start with a B, we had 2 consecutive talks about mass loss. So that is one topic we could talk about. But really any topic. Let me start with Robin Björklund. He claimed in his models there's no biostability jump, which is I think very surprising. Anyone else?
Yes, I guess it was surprising to see a lack of a biostability jump, which is it's also hard to see. Of course, we want to see if this actually occurs in the universe, right? And of course, we have seen potential evidence for a biostability jump, mainly looking at terminal wind speeds. But concerning the mass loss rates there, it's always quite ambiguous to see if there's actually an increase at such an effective temperature. It might help to shed some light if there's more observation for these kinds of B-type stars to see what mass loss rates we get for those.
Yeah, I would have expected a discussion today about the size of the biostability jump and whether it's observed or not, but not on the complete absence. And the reason is that the biostability jump has been predicted not just by Monte Carlo models, but also by Katichka and CMF-Gen models with Petrov. And so I'm really quite surprised you're not finding it.
I mean, I can also, of course, comment, just add to this. I mean, yeah, it was quite surprising, but the reason we don't find it is really because of the yeah, Robin mentioned this during the talk, right? You can't really drive the wind through the sonic point and initiate the higher mass loss rate, even if you get a little bit of an additional force from the recombination. You don't get through actually. So you're basically forced in order to make the model dynamically consistent, you're forced to reduce the mass loss such that it more or less follows the same scaling relations. And at least to our knowledge, in all the previous models, there were always certain tricks played with the dynamics in order to get out the higher mass loss, so to say, both in Petrov and of course in your Monte Carlo models. But so I would say it's a dynamical effect in that sense. With respect to the observations, I don't know if Marimar, Paco's PhD student, is here. She has done some very interesting work on trying to obtain empirical mass loss rate across the bistability jump from radio rates, because they're pretty clean, at least as upper limits. I don't know if Marimar is around actually today to comment on that.
Let's first go to Irji Kirchka. He has his hands up.
Yeah, he has his hands up. Yeah.
Yeah, I'm quite also surprised that you haven't found this bistability jump, because also from our CMF calculations, that the bistability jump is clearly there. So the point is that you recombine iron 4 to iron 3, and iron 3 is quite efficient wind driver. So that's what we get also in B supergiants. But for example, if you look at main sequence B stars, which have a much lower mass loss rate, you do not find any bistability jump because there is no contribution of iron. So I'm wondering, maybe you do not have such contribution of iron, and that's the reason why the bistability jump is not there in your calculation. So it will be really, I think, important to compare the models, to look what are the optical depths of individual lines, and to see why is such a big difference.
Yeah, I mean, yeah, of course. Sorry, Robin, for jumping in. Again, we do see the effect from the recombination from iron. But the point is with the dynamics. It's not really with the radiation driving, but you have to combine this with to make your model dynamically consistent. And unless you play some pretty severe tricks around the critical sonic point region, you simply don't get out. So even if you recombine, we do recombine in our models. Of course, Robin can comment on this. When we go to too high luminosities, your highest luminosities, Robin, that you have calculated, perhaps you can say that, and then what happened? I mean, when you go to even higher, then you get to that. But
yeah, exactly. Yeah, the highest luminosity for that we include in our grid is 10 to the 6th. So for models higher than that, we cannot compute masses or consistent wind models yet, because we simply try to drive too much mass, and this causes sometimes non-monotonic velocity fields which we cannot address yet. So we need to see if we can tackle these inner wind regions for also these high luminosity stars as well.
About 10 to the 6 should be enough to show this bistability if it's appearing to take place. I mean,
I think I agree. But indeed, for these 10 to the 6 models, they indeed do converge. And yet we do not have any increase for the mass loss rate for those, even though we still find a contribution, or like around the sonic point, we have iron 3 and not iron 4. So we do have, we should have this added contribution from the lines of iron 3, but still it does not help to drive higher mass loss rates.
If I may jump in, from the at the very high luminosity end, we have LBVs in this temperature range, and we have the advantage that we see the same star crossing from one side to the other side, so we don't need to look at a large sample of stars. And for AGCAR, we saw a clear trend in of showing the bistability regime, which is interesting. So something that I'll be looking forward to reading in your papers, whether this is a function of the gamma parameter or not.
Very good. There was quite a lot of discussion on Westerlund 1, and I didn't want to necessarily. I think Huuk was going to ask a question.
Well, IFEMA is still around. First,
Are you there, Emma? Yes.
First, I mean, that was a great talk, very nice and very convincing work. Of course, it's a shame that we can't use Westerlund 1 because it would have been a great probe of to test our stellar models. And second, I mean, I noticed that in your HUD, there seems to be as many, well, it's not your HUD, it's the HUD of Westerlund 1. There seems to be as many red supergiants as yellow supergiants. And I was wondering whether you had an explanation for that.
No, basically we don't know. Like that was yeah, because there's 6 of them, right, and 4 red supergiants. That is pretty weird, but
yeah,
they definitely need to be looked at more. But I'm assuming something binary related, but maybe.
A while ago, each time there was something weird, it was magnetic field, but now it seems to be binary.
Well, could work.
So perhaps the people who were looking at the binary fractions in cool supergiants, they maybe something to say about it. Nathan.
Well, maybe the question is whether binary interaction can stabilize a star in the Hertzsprung gap, because that's what you need to have many yellow supergiant, right? Maybe a theoretician should jump in.
Well, I didn't have a comment about that specifically, but I did want to raise another question about Westerlund 1 that maybe someone, this is probably appropriate for the discussion because maybe someone here knows about it, but you know, for an age of 5 million years, it's surprising that, as far as I know, there is not an associated or a lot of molecular gas nearby or giant molecular cloud and a lot of, you know, H2 region emission associated with Westerlund 1 as compared to some other, you know, young, very massive clusters. So if anyone knows about that, if they, you know, survey the region and looked for cold dust and molecular gas that might be associated with the cluster, you know, for something that would make more sense if there's a lack of it, it would make more sense for ages of 7 or 8 or 10 million years rather than 5. So maybe someone can speak to that. Nobody knows if there's any molecular gas near Westerlund 1.
There's not enough star formation people here, apparently.
Well, Ignacio probably is the best person to comment, but it's certainly true that it seems to have evacuated a large region around it. So it's almost certain that given the amount of mass that has gone into it, you probably are looking at some, you know, some event. This is maybe potentially a distance of 4 kiloparsec, you know, at the edge of the kind of galactic bar. So if somehow a large amount of gases come together to all go into the cluster to form that with not much left over, and anything has been left over is clearly being pushed out by previous winds and supernovae. Clearly it's got a magnetar in there, but certainly I think Ignacio, of course, Simon Clark would have been able to comment best on this, but Ignacio might be able to comment more than my recollection, which was that it's evacuated the region of, you know, 10 or tens of parsec around it. So again, I'm fully behind an older age of, you know, 7, 8, maybe 10 at a extreme push. But again, you know, if you are looking at 2 things coming together, there's it's quite likely that maybe has been some extended region. Although Ignacio, I'm afraid Ignacio's mic isn't working. Is that, you know, the certainly from the OB, and that's generally late O, early B supergiants, you know, there's not evidence for a major spread. But I guess just to repeat what I said earlier, the Wolf-Rayet are all binaries, and therefore you know, you tend to, you get an older age with binary channels and you get through single star, as Emma showed.
And a follow-up point would be whether anyone knows if there's evidence for, you know, a whole bunch of recent supernovae from diffuse X-rays or other evidence.
I'm not aware of anything. Ignacio might put something in the chat. Like I said, the magnetars is the only recent, where recent is, you know, 10 to the 4 years. Anything else would have been more distant, and basically you lose a memory after a certain point, don't you?
Sally?
Yeah, I mean, just to concur that having an older age would be more consistent with having the region evacuated, but this thing is in the galactic plane, so I think that that's part of our ignorance of what's happening. But my question was also about comparing this to the Carina star-forming region, because that certainly has Wolf-Rayet stars and LBVs in it too. And whether anybody knows how that region compares, and whether this problem with the ratio of yellow supergiants to red supergiants is also seen in Carina.
I suppose I could comment on that. I mean, there are no red supergiants and no yellow supergiants in Carina. The three Wolf-Rayet stars are not normal Wolf-Rayet stars. They're these hydrogen-rich WNH stars that are supposedly, you know, very massive main sequence stars still. And the Carina region is consistent with a much younger age, something closer to 3 or maybe 4 million years. And there is a ton of molecular gas and lots of H2 region emission, of course, which is all of those are very different from Westerlin 1.
Interesting.
Roman Lopez.
Yeah, hi. Just a comment on what Nathan just mentioned about some clue or some hint about the gas or molecular contribution from the sun of the galaxy. I just took a look on the Aladdin image on 6 centimeters and 21 centimeters, and it seems that Westerlin 1 has a point source. It appears like a point source on 21 centimeters. Of course, the resolution of this survey is not enough to reveal if there's something round or just, but we see clearly a point source in this at this position. Just a comment on it.
All right. I think we can continue these discussions in the breakout rooms.